Now here the question is, we are given this function fx which is mod of x minus 2 plus a square minus 6a plus 9 if x is less than 2, and it is 5 minus 2x when x is greater than or equal to 2. Now it says if this limit x tends to 2, greatest integral function of fx, it exists, then find the possible values of a. Now we know that for this limit to exist, right limit must be equal to its left hand limit. Now first we are going to write its right hand limit. So it will be this limit x tends to 2 positive, and here it will be this greater function of 5 minus 2x. We let x as 2 plus h, so it will be this limit h tends to 0 positive, and then 5 minus 4 minus 2h, which is 1 minus 2h, and 1 negative is 0, so its greater function is 0, so its right hand limit is 0. Now if its right hand limit is 0, its left hand limit must also be 0. So if we write its left hand limit, which is limit x tends to 2 negative, so it will be this greater function of x minus 2 plus a square minus 6a plus 9. Now we'll put x as 2 minus h, so it will be this greater function of a square minus 6a plus 9 plus h, and it must be equal to 0. Now this is true when a square minus 6a plus 9, it is greater than 0 but less than 1. Now this is a minus 3 whole square, which is always greater than or equal to 0. So from here we'll get minus 1, a minus 3, 1, or value of a should lie between 2 and 4. So all the values of a which lies between 2 and 4 are going to satisfy this condition. So all the values that lie between 2 and 4 are 2.5, 3 and 3.5. So the correct options are B, C and D. Now here the question is, we are given this function fx which is x plus 3 when x lies between minus 2 and 0, 4 when x is equal to 0, and 2x plus 5 when x lies between 0 and 1. Now first question is, we need to find this limit x tends to 0 negative f greatest integral function of x minus 10x. Now if we look at graph of y equals x and y equals 10x, then when x is negative, then in that case x is greater than 10x. That means x minus 10x is greater than 0. But this value, it lies between 0 and 1. Therefore, its greatest integral function x minus 10x will take the value 0. So this limit will be equal to f0, and f0 is 4. That means the correct option is this option B. Now the next one is limit x tends to 0 positive f fractional part of x upon 10x. Now we know that when x is positive, then x is less than 10x, or x upon 10x, it is less than 1. Now when h lies between 0 and 1, then fraction part of h is same as h. So that means this limit, it will be simply limit x tends to 0 positive f x by 10x. Now x by 10x is actually less than 1, and if it is less than 1, it will go to this definition. So we can write this as limit x tends to 0 positive 2 times x upon 10x plus 5, which is 7. So answer to the second part is 7, and that's your option C. Now here this first question is, if limit x tends to 0, log cot pi by 4 minus beta x upon 10 alpha x equals 1. Find the value of alpha upon beta. Now we put x as 0. This is log 1 0, 10 0 0, which is 0 upon 0 form. So we'll use L'Hopital's rule. So it will be this limit x tends to 0. Now log is 1 upon x and 1 upon x is 10. So it will be this 10 pi by 4 minus beta x, and then derivative of cot is minus cosec square pi by 4 minus beta x, and then into minus beta upon, now derivative of 10 is secant square. So it will be secant square alpha x into alpha, and this is equal to 1. Now we'll put x as 0. Now 10 pi by 4 is 1. Now cosec pi by 4 is root 2. So it will be this minus 2 and then minus beta upon alpha equals 1. So value of alpha upon beta will be 2. So answer to this question is 2. Now the question is, if limit x tends to 0, fx upon sin square x equals 8. Now it has to be 0 upon 0 form. That means f0 is 0, and also this limit x tends to 0, gx upon 2 cos x minus x into e to the power x plus x cube plus x minus 2. Now if we put x as 0, so it is 2 minus 2 0, 1 minus 1 0, so which again is 0 upon 0 form. This is lambda, and we also know g0 is equal to 0, and we are given that this limit x tends to 0, 1 plus 2 fx to the power 1 upon gx, it is e to the power minus 1. Now this is 1 to the power infinite form. If we use shortcut, we can write this as e to the power limit x tends to 0, 2 fx upon gx, it is equal to e to the power minus 1. So from here we can write this limit x tends to 0, fx upon gx, this value will be minus 1 by 2. Now we need to find the value of lambda. Now what we'll do is, we'll divide these two limits. Now if we divide them, we can write limit x tends to 0, fx upon gx into 2 cos x minus x into e to the power x plus x cube plus x minus 2 upon sin square x, and will be equal to 8 upon lambda. Now we have already worked this out. This is minus 1 by 2, so it will be this minus 1 by 2, and then this limit x tends to 0. Now we write this as minus 2 1 minus cos x minus x into e to the power x minus 1 plus x cube upon sin square x, and it is equal to 8 upon lambda. What we'll do is, we'll divide numerator and denominator with x square. So this is x square, this is x square upon x square. Now this is minus 1 by 2. Now 1 minus cos x upon x square is 1 by 2. So this is minus 1. Here e to the power x minus 1 upon x is 1. X will cancel. So this is minus 1 plus 0 upon this is 1. That is equal to 8 upon lambda. So clearly value of lambda is 8. And that is the answer to this question. Now here the question is, if alpha and beta are two distinct real roots of this equation, ax cube plus x minus 1 minus a equals 0, where a is unequal to minus 1 or 0, and alpha and beta, they are unequal to 1, then we need to find the value of this limit. Limit x tends to 1 by alpha 1 plus a x cube minus x square minus a upon e to the power 1 minus alpha x minus 1 into x minus 1. Now if we put x equal to 1 in this equation, we'll get a plus 1 minus a equals 0. That means one of the roots of this equation is 1. So roots of this equation are 1, alpha and beta. Now we'll find the equation whose roots are 1 upon alpha and 1 upon beta, and for that we'll replace x with 1 upon x. So it'll be this a upon x cube plus 1 upon x minus 1 minus a equals to 0, or we can write this equation as 1 plus a x cube minus x square minus a equals 0. So if we take this limit x tends to 1 by alpha, then 1 plus a x cube minus x square minus a, it will be 0 as 1 upon alpha is one of the root of this equation. So basically now we know that this equation has 3 roots, 1 upon alpha and 1 upon beta. So we can write this limit L as limit x tends to 1 by alpha, and if factorize it, we can write this as 1 plus a into x minus 1 upon alpha, x minus 1 upon beta upon e to the power 1 minus alpha x minus 1 into x minus 1. Now this x minus 1 will cancel. We can write this as limit x tends to 1 by alpha. Now it will be this 1 plus a. Here we'll take minus common. So it will be this minus and then 1 minus alpha x, and here will be this beta x minus 1 upon e to the power 1 minus alpha x minus 1 into alpha beta. Now this is standard limit e to the power x minus 1 upon x. So it is 1, and we'll put x as 1 upon alpha. We can write this limit L as minus 1 plus a beta upon alpha minus 1 upon alpha beta, or it is 1 plus a into alpha minus beta upon alpha square beta. So value of this limit is 1 plus a into alpha minus beta upon alpha square beta. Now 1, alpha and beta, they are roots of this equation. So if we find their product, 1 into alpha into beta, it is minus c upon a, which is 1 plus a upon a. So we'll put alpha beta as 1 plus a upon a. So it will be 1 plus a into alpha minus beta upon alpha, and it will be 1 plus a into a. So it will cancel. So value of this limit, it will be a into alpha minus beta upon alpha. Now we compare it with this given limit, then we can write value of L must be 1, value of K must be 1. Now we need to find the value of K into L. Value of K into L is 1. Now here the question is, find this limit x tends to alpha positive, that is minimum of sin x and fractional part of x upon x minus 1, where alpha is the root of the equation, sin x plus 1 equals x, where these are greatest integer and fractional part functions respectively. Now if we draw the graph of sin x and fractional part of x, that's the graph of sin x. Now this is 0, this is 1, 2 and 3, between 0 to 1, this is x. Then we have one solution here, then we have one more solution here and one more here. Whichever solution we take, if this is alpha, then in the neighborhood of alpha positive, fractional part of x will always be greater than sin x. So that means this minimum of sin x and fractional part of x will always be sin x. So we're going to write this limit as limit x tends to alpha positive greatest near function of sin x upon x minus 1. Now we know that at this point it is sin x plus 1 equals x. Now beyond that we know that fractional part of x will be greater than sin x and fractional part of x is x minus 1. So x minus 1 will be greater than sin x. So we can write sin x upon x minus 1 will be less than 1. And if it is less than 1, then its greatest near function value will be 0. So value of this limit is 0, and that is the answer to this question. Now here the questions, we are given this fx is cos 2x, cos 4x, cos 6x, cos 8x and cos 10x. Then we need to find this limit x tends to 0, 1 minus fx cube upon 5 sin square x. Now f0 is cos 0 5 times, so it will be this one. So it is 1 minus 1 0, sin 0 is 0, so it is 0 upon 0 form. Now we can write this as limit x tends to 0, and we write this as 1 minus fx, and here will be f square x plus fx plus 1 upon, and we write this as 5x square and then sin square x upon x square. Now this is 1 and this value is 3, so we can write this limit as limit x tends to 0, 3 into 1 minus fx upon 5x square, which again is 0 upon 0 form. Now we'll write this as limit x tends to 0, and this is 3 into 1 minus, now fx is cos 2x into cos 4x into cos 6x cos 8x into cos 10x whole divided by 5x square. Now what we'll do is we'll use expansion formula for cos. So we can write this as limit x tends to 0. Now this is 3. It is 1 minus 2 square x square upon 2. Higher powers 1 minus 4 square x square upon 2. 1 minus 6 square x square upon 2. 1 minus 8 square x square upon 2. And then 1 minus 10 square x square upon 2 and higher powers divided by 5x square. Now we multiply it, then we can write this as limit x tends to 0. This is 3, 1, and then 1 into 1 into 1 5 times, so it will be 1 minus 1, and then we need to find coefficient of x square. Now we'll get x square if this x square gets multiplied with all these ones. Now this is minus minus plus, so it will be plus 2 square upon 2 plus 4 square upon 2 plus 6 square upon 2 plus 8 square upon 2 plus 10 square upon 2 x square upon 5x square. Now here 1 and 1 will cancel. Now minimum power of x in the numerator is x square, and in the denominator it is also x square. So answer to this limit will be coefficient of x square in the numerator and in the denominator. So it will be this 3, and this is 2 plus 8 plus 18 plus 32 plus 50 divided by 5. Now this is 10 and 40, 50. Now this is 10 and 50. So it will be 3 into 110 divided by 5. Now this is 22. So answer to this limit is 66. And that's your option D. Now here the question is, we need to solve this limit, which is limit x tends to 0, and then this summation greatest negative function of r square sine inverse rx upon x, where r varies from 1 to n. Now we know that when x tends to 0 positive, sine inverse rx, it is greater than rx. So basically sine inverse rx upon rx will be greater than 1, and if we multiply r cube, then we can write r cube sine inverse rx upon rx will be greater than r cube. So this value, it is r cube plus h. So greater function of r square sine inverse rx upon x, it is equal to this summation r varies from 1 to n r cube, and it is equal to 100. Now this is n plus 1 upon 2 whole square, and this is 100. So we can write n plus 1 will be equal to 20, which is 5 into 4. That means value of n is equal to 4. So n is 4, and that is answer to this question. Now here the question is, we are given this function f defined from r to 0 to infinite such that fx plus e to the power x plus x square upon fx, it is less than equal to e to the power x plus e to the power x square for all x greater than 0. Now since fx is positive, we can rearrange this inequality as f square x minus e to the power x plus e to the power x square fx, and plus e to the power x into e to the power x square. It should be less than equal to 0. Now we can factorize this as fx minus e to the power x into fx minus e to the power x square, and it will be less than equal to 0. So from here we can write this fx, it belongs to this interval e to the power x and e to the power x square. Now whatever may be the order, if we take this limit x tends to 1, this limit is e and this limit is also e, then from sandwich theorem we can say this limit x tends to 1 fx, it is e, and that's your option C. Now here the question is, we are given this function fx in terms of greatest integer function and fraction part function. Now when x is greater than 0, fx is defined as, so this first case, when x is greater than 0, fx is equal to this limit n tends to infinite px by n, and then this summation where r varies from 1 to n, and it will be this greatest linear function of r square plus r minus e to the power minus x minus 1 upon r plus 1 plus lambda. Now since r is an integer, we can write this as limit n tends to infinite px by n, and then this summation r varies from 1 to n, and we know that greatest linear function of x plus n is greatest linear function of x plus n if n is an integer. So it will be this r square plus r minus 1, and then plus this greatest linear function of minus e to the power minus x upon r plus 1 and plus lambda. Now when x is greater than 0, e to the power minus x, it lies between 0 and 1, and then minus e to the power minus x will lie between minus 1 and 0. So greatest net function of minus e to the power minus x, it will be minus 1. So we can write this as limit n tends to infinite px by n, then this summation r varies from 1 to n and will be r square plus r minus 2 upon r plus 1 plus lambda, which we can also write as this limit n tends to infinite px by n summation 1 r varies from 1 to n and then minus 2 summation 1 upon r plus 1 plus lambda. Here r varies from 1 to n. Now this is limit n tends to infinite. This is px by n. Now this is n and this is minus 2, and we can write this as this summation r varies from 1 to n, and here it will be 1 upon r minus 1 upon r plus 1 plus lambda. So we'll write this as limit n tends to infinite px by n into n minus 2, and here it will be 1 minus 1 upon n plus 1 plus lambda, that we multiply it, then we'll get this as px plus lambda. So this function fx is px plus lambda when x is greater than 0. At x equal to 0, it is q. Now we need to find the definition when x is less than 0. Now if x is less than 0, it is given as this limit n tends to infinite, this summation r varies from 1 to n, fractional part of r square plus r plus e to the power x minus 1 upon r plus 1. Now we know that fractional part of x plus n, it is equal to simply fractional part of x. So we can write this as limit n tends to infinite, this summation r varies from 1 to n. All these integer, they will be removed, so it will be simply fractional part of e to the power x upon r plus 1, and also when x is less than 0, e to the power x lies between 0 and 1, so its fractional part will be same as e to the power x. So it will be this limit n tends to infinite e to the power x, and then this summation r varies from 1 to n, 1 upon r minus 1 upon r plus 1, which is this limit n tends to infinite e to the power x 1 minus 1 upon n plus 1, which is nothing but e to the power x. So this function will be q when x equal to 0, and it will be e to the power x when x is less than 0. Now it says it is differentiable in R. If it is differentiable in R, then it must be continuous at 0. And if it is continuous at 0, that means lambda equals q and will be equal to e to the power 0, which is 1. So value of lambda is 1 and value of q is also 1. Now it must also be differentiable. Now if we find f dash x, it will be p when x is greater than 0 and will be e to the power x when x is less than 0. So in that case, this p, it is equal to e to the power 0, which is 1. So the value of p plus q plus lambda is 3, and that's your option D. Now the second question is find the value of f dash log 2, f dash log 1 by 2, f dash log 3 upon 2 square up to infinite. Now we know that f dash x, it is 1 when x is greater than 0, and it is e to the power x when x is less than 0. Now at log 2, this value is positive, so this is 1 plus, now all these log 1 by 2, log 3 upon 2 square, log 5 upon 2 cube, this x is less than 0. So for all these, it will be this e to the power x. So it will be this e to the power log 1 by 2 e to the power log 3 upon 2 square up to infinite. So we need to find some of this series, which is 1 plus 1 by 2 plus 3 by 2 square plus 5 by 2 cube up to infinite. Now we'll write this series once again, leaving one term. So it will be this 1 by 2, 3 by 2 square, and we'll multiply it with common ratio, that is 1 by 2. Now if we subtract, we'll get this as s by 2, and here will be 1 plus, and this is 2 upon 2 square, 1 by 2. This is 2 upon 2 cube, 1 upon 2 square up to infinite. Now this is a upon 1 minus r, which is 2. So sum of this series is 4, and that's your option B. Now this third question is, if G is inverse of f, then G dash 1 by 2 is. Now we know that fx is e to the power x when x is less than 0. So if we look at f log 1 by 2, f log 1 by 2 will be e to the power log 1 by 2, and that is 1 by 2. So that means f log 1 by 2 is equal to 1 by 2. Now we know that if fx and gx, they are inverse function of each other, then g of fx, it is equal to x. Now we differentiate, we can write g dash fx into f dash x, it must be 1, and what we'll do here is we'll put x as log 1 by 2. So here it will be g dash and f log 1 by 2 into f dash log 1 by 2, and it is equal to 1. Now we already know that f log 1 by 2 is 1 by 2. Now f dash log 1 by 2. Now log 1 by 2 is less than 0. So f dash x is e to the power x. So it will be e to the power log 1 by 2, which is 1 by 2, and this is 1. So from here we can say value of g dash 1 by 2 must be equal to 2. And that's your option C. Now the question is, find the possible value of k for which this limit is equal to 1 by 2. Now what we'll do is we'll divide everything with x cube. So we can write limit x tends to infinite 2 minus tan inverse x upon x whole cube, and here it will be 8 upon pi cot inverse mod kx plus k square. Now will be sine 1 by x cube, and here we have x cube, which we are going to write as 1 by x cube, and here it is minus 3k, and it is equal to 1 by 2. Now we'll take this limit x tends to infinite. Now this is 2 minus, now tan inverse infinite is pi by 2, and pi by 2 upon infinite is 0. Here this is cot inverse infinite. Now cot inverse infinite is 0, so this is 0. Here sine x upon x, when 1 upon x cube tends to 0, it is 1. So it will be this k square minus 3k, that is equal to 1 by 2. So from here we can write k square minus 3k minus 4 equals 0. So it will be this k minus 4 into k plus 1 equals 0. So value of k is either minus 1 or value of k is 4. That means the possible values are minus 1 and 4. Options B and D. Now we have this case when we have assumed that this k is unequal to 0, because this expression cot inverse kx will make a difference whether k is 0 or non-zero. So we have to consider one more case, considering k equals 0. Now if k is 0, we'll have cot inverse 0, and cot inverse 0 will be pi by 2. in that case we'll have this limit x tends to infinite 2 minus 0. Now this is 8 upon pi into pi by 2. There will be 4 plus k square minus 3k, and if k is 0, this value is again going to be 1 by 2. So that means one more value of k is possible. So there are 3 values possible for k, which are 0, minus 1 and plus 4. Now here the question is, we are given this function fx and it says f0 positive is p and f0 negative is q. Now p is limit x tends to 0 positive, and it is pi by 2 minus cos inverse 1 minus fractional part of x square into cos inverse 1 minus fractional part of x whole square, and this is 2 times fractional part of x minus fractional part of x whole cube. Now what we'll do is we'll let x as 0 plus h, and we know that fractional part of h is simply h. So it will be this limit h tends to 0 positive, and pi by 2 minus cos inverse x is sine inverse. So it will be this sine inverse 1 minus h square into cos inverse 1 minus h whole square whole divided by, now we'll take h common, and then it will be 1 minus h square. We don't have problem with this because it is sine inverse 1 pi by 2 and this is simply 1. So we are going to write this as limit h tends to 0, and here will be this pi by 4, and then we have cos inverse 1 minus h square upon h, which is 0 upon 0 form. Now here what we'll do is we'll let 1 minus h as cos theta. Now when h tends to 0, cos theta tends to 1, that is theta tends to 0. So we write limit theta tends to 0. This is pi by 4, and will be theta square, and this is 1 minus cos theta. Now 1 minus cos theta upon theta square is 1 by 2. So this value is simply pi by 2. So value of p is pi by 2. Now we'll find q, which is its left hand limit. So it will be this limit x tends to 0 negative, and then it is pi by 2 minus cos inverse. We have to write directly as sine inverse 1 minus fraction part of x square, and then cos inverse 1 minus fraction part of x square upon 2, and this is fraction part of x minus fraction part of x whole cube. Now we let x as 0 minus h, and then fraction part of minus h is 1 minus h. So it will be this cube, and limit h tends to 0 positive, and it will be this sine inverse 1 minus, and it will be this 1 minus h whole square. Here it will be cos inverse 1 minus h whole square. Here it will be 2 into, we'll take 1 minus h common, and then it will be 1 minus h whole square. Now this is 0 upon 0 form, sine inverse 1 minus h square. So it will be this one, and here we have cos 0, and cos 90 is 0. So it will be this pi by 2 square and into 2. So it will be this pi square by 8. So we have p equals pi by 2 and q equals pi square by 8. Now we need to find the value of p pi by q. Now p is pi by 2, so this is pi square by 2, and q is pi square by 8, so this value is 4. So answer to this question is 4. Now here the question is, If alpha and beta are roots of this equation, then find the value of 8 to the power alpha plus 2 to the power beta minus alpha beta. Now this is infinite limit. So the highest power of t in the numerator is t to the power 1 by 2, and the denominator also it is t to the power 1 by 2. If we cancel it, we can write this as limit t tends to infinite cos inverse sine tan inverse, and here we'll get this as under root x upon x square minus 3x plus 1 minus 1 upon t minus x upon under root t, and this is equal to pi by 6. Now when t tends to infinite, 1 upon t tends to 0. So we can write cos inverse sine tan inverse under root x upon under root of x square minus 3x plus 1. It is equal to pi by 6. Now we take this cos inverse on the right hand side. It will be cos pi by 6, which is root 3 by 2. Now sine inverse root 3 by 2 is pi by 3. And if we take this 10 on the right hand side, 10 pi by 3 is root 3. So we'll get this as 3x square minus 9x plus 3, and it is equal to x, or 3x square minus 10x plus 3 equals 0. Now this is 3x minus 1 and x minus 3 equals 0. So value of x is either 1 by 3 or 3. So there are two roots. Now alpha is smaller, so alpha is 1 by 3 and beta is 3. Now we need to find the value of 8 to the power alpha. So this is 8 to the power 1 by 3 plus 2 to the power beta minus alpha beta, which is 1. Now this is 2 plus 8, 10. 10 minus 1 is 9. So answer to this question is 9. Now here the question is, we are given the series Sn, which is this summation r varies from 1 to n, and this is tan inverse. Now if we divide everything with 4, we can write this as 2r minus 1 by 2 upon 1 minus r square and r minus 1 whole square by 4. Now we can simplify this as this summation r varies from 1 to n, and will be this tan inverse r by root 2 square minus r minus 1 by root 2 square, and here it will be 1 plus r by root 2 square and r minus 1 by root 2 whole square. Now this is tan inverse x minus y upon 1 plus xy. So we can write this as this summation r varies from 1 to n, tan inverse r by root 2 square minus tan inverse r minus 1 by root 2 square. Now if we put the value of r, we can write this as tan inverse 1 by root 2 minus tan inverse 0 plus tan inverse 2 by root 2 square minus tan inverse 1 by root 2 square, and in the end we'll have tan inverse n by root 2 square minus tan inverse n minus 1 by root 2 whole square. Now here all these terms they'll cancel. So basically we'll get this Sn as tan inverse n square by 2. Now we need to find this limit. N tends to infinite. This summation n varies from 2 to n cot Sn minus 1 minus cot Sn. Tan inverse n square by 2 is cot inverse 2 by n. So we can write this as limit n tends to infinite, and then this summation n varies from 2 to n, and here it will be 2 upon n minus 1 square, and this one is going to be 2 upon n square. Now if we put the value, we can write this as 1 upon 1 square minus 1 upon 2 square, 1 upon 2 square minus 1 upon 3 square up to, now all these terms they'll cancel. So this sum s dash n will be given by 2 into 1 minus 1 n square. Now we need to find this limit n tends to infinite. Now we take this limit n tends to infinite. Now this is just 2. So answer to this question is simply 2. Now the question is limit n tends to infinite 1 plus cn square upon 2n plus 3 plus 2 sine n whole square, and it is 1 by 2. Now we divide everything with n square. We can write this as limit n tends to infinite 1 upon n square plus c, and here it will be 2 plus 3 upon n plus 2 sine n upon n whole square, and this is 1 by 2. Now we put n tends to infinite, this is 0 plus c, and this is 2 plus 0. Now this is sine infinite upon infinite. Now sine infinite is oscillating value, which is minus 1 to 1. So minus 1 to 1 upon infinite is 0. So this is 2 plus 0 whole square, and it is 1 by 2. So value of c is simply 2. So from here we'll get the value of c as 2. Now it says both the roots of this equation, alpha and beta, they are greater than 2. So we have to find the condition that both roots are greater than 2. Now if we look at this equation is x square minus 2px plus p square minus 1 equals 0. Now this is x minus p whole square minus 1 equals 0. So the roots of this equation are p minus 1 and p plus 1. So we have these roots as p minus 1 and p plus 1, and these roots, they must be greater than 2, which means this p minus 1, it must be greater than or equal to 2, or p is greater than or equal to 3. Now the smallest integral value of p is simply 3, and that is the answer to this question. Now here the question is, this fx when x is unequal to 0 is continuous at x equal to 0. Find the value of f0 plus 2 lambda. Now if we look at this fx, and if we look at f0 negative, then when x is 0 negative, then 1 plus x is 1 negative, that is, it is less than 1. And if it is less than 1, then 1 plus x to the power n, it approaches 0 as n tends to infinite. So in that case, we can write this as this limit x tends to 0 negative. Now in this case, this is 0 and this is 0. So it will be simply lambda sine n minus under root of n square minus 8n into x whole divided by x, and it is also given that limit n tends to infinite. Now we rationalize this, we can write this as limit x tends to 0 negative, limit n tends to infinite. Now this is lambda sine, and here it is n square minus n square plus 8nx upon n plus under root of n square minus 8n, and this x is out of this brackets. Here n and n will cancel, and we also have this x. Now this is infinite limit. The highest power of n in the numerator is 1 and the denominator is also 1. So it will be this limit x tends to 0 negative lambda sine, and here coefficient is 8. So it will be this 8x upon 2. So there will be sine 4x upon x. Now we multiply and divide it with 4. This is also standard limit, and this is 1. So it will be equal to 4 lambda. Now if we look at f0 positive, in that case 1 plus x is greater than 1. So 1 plus x to the power n is infinite when n tends to infinite. So we have to divide everything with 1 plus x to the power n. Now in that case this will be 0 and this part will be 0. So now we can write this limit as limit x tends to 0 positive, and here it will be 1 minus cos 1 minus 10 pi by 4 minus x whole divided by x square. Now this is 0 upon 0 form. We'll simplify this. Now this is limit x tends to 0 positive. This is 1 minus cos, and it is 1 minus 10x upon 1 plus 10x upon x square, which is limit x tends to 0 positive 1 minus cos, and this is 2 10x upon 1 plus 10x upon x square. Now what we'll do is we'll multiply and divide it with 2 10x upon 1 minus 10x whole square. So it will be 2 10x upon 1 plus 10x whole square. Now this is standard limit 1 by 2, and here 10 square x upon x square will be 1. So we'll have this 4 into 1, and then upon 1 plus 10 0 is 1. So it will be this 1 square. So this value, it is equal to 2. So from here we can say f0 is equal to 4 lambda, and it is equal to 2. So value of 2 lambda is equal to 1. Now we need to find the value of f0 plus 2 lambda. Now f0 is 2 and 2 lambda is 1. So this value is 3. So answer to this question is 3. Now here the question is, we are given this function fx, which is this summation r varies from 1 to n r square x square plus x plus r upon r x square plus 1, its greatest linear function. Now we can write this as this summation r varies from 1 to n, and we'll take these two terms together. We'll take r common. It'll be r x square plus 1 upon r x square plus 1 and plus x upon r x square plus 1. Now here r x square plus 1 will cancel, and since r is an integer, we can simply write this as this summation r varies from 1 to n summation r plus this summation r varies from 1 to n greatest linear function of x upon r x square plus 1. Now summation r is n plus 1 by 2, and then we have to simplify this summation. R varies from 1 to n greatest linear function of x upon r x square plus 1. Now this function is defined from 0 to infinite to n. That means value of x is positive. So what we'll do is we'll write x upon r x square plus 1 as 1 upon rx plus 1 by x, and if we take AMGN, then rx plus 1 by x by 2, it is greater than or equal to under root r, or rx plus 1 by x is always greater than or equal to 2 root r. Now if we take its reciprocal, then we can write x upon rx square plus 1 will always be less than 1 upon 2 root r. That means it is always less than or equal to 1 by 2. Now if it is always less than or equal to 1 by 2, then the value of this greatest limit function will be 0. So basically this function fn, it is nothing but n into n plus 1 by 2. Now we need to find this limit, which is limit n tends to infinite greatest limit function of fx minus n upon fx square minus n cube n plus 2 upon 4, its greatest integer function. Now we're going to write this as limit n tends to infinite, and this is greater than function of, we'll take this n common, and here will be n plus 1 by 2 minus 1, and here it will be n square, n plus 1 whole square by 4 minus n cube, n plus 2 by 4. Now this is limit n tends to infinite, and here it will be n into n minus 1 by 2, and here we'll take n square by 4 common, then we'll have n plus 1 whole square minus n into n plus 2. Now this is limit n tends to infinite, and this is n minus 1 by 2, and here it is n square by 4. Now here n square plus 2n will cancel, so this value will be simply 1. Now this n and n will cancel, this 2 and 4 will cancel twice, so we can write this as limit n tends to infinite to n minus 1 upon n. Now this is limit n tends to infinite, and this is 2 minus 2 by n. Now if we consider this bracket as greatest integer function, then we know that 2 minus 2 by n is less than 2. In that case, value of this limit, it will be 1. And if we consider them as simple square brackets, then this limit will be simply 2 minus 0, and then it will be 2. In some of the books, you'll find this answer as L equals 2. But in the question, since they have mentioned that this box, it represents greatest integer function, so I think answer to this question should be L equals 1. Now here the question is, we need to solve this limit x tends to 0, greatest integer function of minimum of y square minus 4y plus 11 into sine x upon x, where this box represents greatest integer function. Now if we look at y square minus 4y plus 11, we can write this as y minus 2 whole square plus 7. That means it is always greater than or equal to 7. So minimum value of this expression will be simply 7. So we need to find this limit x tends to 0, and then minimum value of 7 sine x upon x. Now we know that sine x is less than x, then sine x upon x, it is less than 1, or 7 sine x upon x, it is less than 7, and therefore its greatest integer function will be 6, and that's your option 2. Now here the question is, let f be a positive increasing function with limits x tends to infinite f3x upon fx equals 1. We need to find this limit x tends to infinite f2x upon fx. Now since fx is positive increasing function, then we know that fx will be less than f2x and will be less than f3x. Now we divide everything with fx, we can write 1 is less than f2x upon fx and will be less than f3x upon fx. Now if we take this limit x tends to infinite, this is 1, and in the question it is given that this limit is also 1. Then from sandwich theorem we can say that this limit x tends to infinite f2x upon fx will also be 1, and that's your option 4. Now the question is, let box x denote the greatest integer function, then find this limit. Now what we'll do is we'll find left hand limit and right hand limit. So its left hand limit will be limit x tends to 0 negative 10 pi sine square x plus mod x minus sine x into greatest function of x whole square divided by x square. Now we'll let x as 0 minus h. In this case, it will be this limit h tends to 0 positive, and this is 10 pi into sine square h plus, now this is h minus sine, now this is minus h, and get a function of minus h is minus 1 whole square upon h square. So this is limit h tends to 0. Now we can write this as 10 pi sine square h upon h square, and plus this is 1 minus sine h upon h whole square. Now if we make it standard limit by multiplying and dividing it with pi sine square h, then we'll get this limit as pi, and here it will be 0. So its left hand limit is equal to pi. Now we'll find its right hand limit. Now its right hand limit will be limit h tends to 0 positive 10 pi sine square x plus mod x minus sine x, and get a function of x in this case is 0 whole square whole divided by x square. So it will be this limit x tends to 0 positive. Now this is 10 pi sine square x upon x square, and then plus 1. Now we have already solved this. This is pi. So this right hand limit will be pi plus 1. Now left hand limit is pi, right hand limit is pi plus 1. Therefore, this limit, it does not exist. And that's your option D. Now here the question is, we need to find this limit x tends to 1 positive 1 minus mod x plus sine mod of 1 minus x into sine pi by 2 greatest net function of 1 minus x upon mod of 1 minus x into greatest net function of 1 minus x. Now what we'll do is we'll let x as 1 plus h. Now will be this limit h tends to 0 positive 1 minus mod of 1 plus h and plus sine, this is mod of 1 minus 1 plus h, and here it will be this sine pi by 2, it is 1 minus 1 plus h upon mod of 1 plus h, and this 1 minus 1 plus h. Now we write this as limit h tends to 0. Now this is 1 minus mod of 1 plus h is 1 plus h, and this is simply sine h. Now here it is sine pi by 2 into greater function of minus h, and greater function of minus h is minus 1. So there will be sine minus pi by 2, which is minus 1. And here this value will be mod h, and mod h is simply h, and here also this is greater function of minus h, which again is minus 1. So this minus and minus will cancel. So we'll get this as limit h tends to 0 positive minus 1 plus sine h upon h. Now sine h upon h is 1. So minus 1 plus 1 is 0. So value of this limit is 0, and that's your option A. Now here the question is, we need to find this left hand limit, which is limit x tends to 0 negative, and this is x into greater function of x plus mod of x sine greatest greater function of x upon mod of x. Now we let x as 0 minus h, and we know that greater function of minus h, it is minus 1. So it will be this limit h tends to 0 positive. Now this is minus h. Here this is minus 1 plus h, and this is sine minus 1, and this is h. Now h and h will cancel. This value will be simply minus sine 1, and that's your option C. Now here the question is, we're given that limit x tends to 0 positive, x into this summation greatest real function of r by x, where r varies from 1 to 15. Now we know that any greater function, it is less than equal to x, but greater than x minus 1. So we can write this greater function of r by x will be greater than r by x minus 1, will be less than equal to r by x. Now if we multiply it with x, we can write r minus x will be less than x into r by x, and will be less than or equal to r. Now we'll take this summation. R varies from 1 to 15. Now this is n plus 1 by 2 minus 15x, and it will be this summation r varies from 1 by 15 x into greatest function of r by x, and will be less than equal to 15 by 8. Now if we take this limit x tends to 0, this is 120, this also is 120. Then from sandwich theorem we can say that this limit is equal to 120, and that's your option C. Now here the question is, we need to find this limit x tends to 1 positive fx, which is 1 minus x into 1 plus mod of 1 minus x upon mod of 1 minus x into cos 1 upon 1 minus x. Now what we'll do is we'll let x as 1 plus h, so it will be this limit h tends to 0, and this is 1 minus 1 plus h, and here it is 1 plus mod of 1 minus 1 plus h, and this is mod of 1 minus 1 plus h, and here also it is cos 1 upon 1 minus 1 plus h. Now this is limit h tends to 0. Now this is 1 minus 1 plus h. Now here 1 and 1 will cancel, so this also is 1 plus h. Here this value is h, and this is cos 1 by minus h, which is cos 1 by h. Now this is limit h tends to 0. Now 1 minus 1 will be 0, and then it will be minus 2 plus h into cos 1 by h. Now this minus 2 into cos 1 by h will be minus 2 into cos infinite, which is oscillating value between minus 2 and plus 2. That means this limit, it does not exist. So limit x tends to 1 positive fx, it does not exist. Now what about limit x tends to 1 negative. If we take limit x tends to 1 negative fx, we let x as 1 minus h. Now in this case, it will be this limit h tends to 0 positive, and this is 1 minus h, and here this value will be 1 plus h upon h, and it will be cos 1 by h. Now this is a plus b, a minus b. So this one will cancel. This value will be h cos 1 by h, which is 0 into oscillating value minus 1 to plus 1, which is 0. So limit x tends to 1 negative fx will be 0. That's your option C. Now here the question is, we are given this limit x tends to 0, 1 plus x log 1 plus b square to the power 1 by x. It is 2b sine square theta, where b is greater than 0. Now this is 1 to the power infinite form. We'll use shortcut, so it will be e to the power, and then it will be this limit x tends to 0, 1 by x, and then x log 1 plus b square, and it is equal to 2b sine square theta. Now x and x will cancel. Now this is 1 plus b square equals 2b sine square theta, or we can write b plus 1 upon b by 2, it is equal to sine square theta. Now b plus 1 upon b by 2, it is greater than or equal to 1 using am and gm. Whereas, so this left hand side, it is 1 or greater than 1, and your right hand side, which is sine square theta, it is always less than or equal to 1. So the only case where this left hand side can be equal to right hand side is when both of them they are 1. And if both of them they are 1, then value of b is 1, and sine square theta equals 1 means theta is plus or minus pi by 2. That means this option D is correct. Now here the question is, we are given this function gx, which is x minus 1 to the power n upon log cos to the power m x minus 1 when x lies between 0 and 2, where m and n are integers, and m is equal to 0 and n is greater than 0. Now p is left hand derivative of x minus 1 at x equals 1. Now if we look at this function, x minus 1 will be minus x plus 1 when x is less than 1, and it will be x minus 1 when x is greater than or equal to 1. So if we look at its left hand derivative, f dash 1 negative, will be simply minus 1. So that means value of p is minus 1. Now it says limit x tends to 1 positive gx is p. So this limit x tends to 1 positive x minus 1 to the power n, and here we'll take this power out, so it will be m log cos x minus 1, and this is equal to minus 1. Now this is 0 upon 0 form. We'll use L'Hopital's rule, so it will be this limit x tends to 1 positive, and this is n x minus 1 to the power n minus 1, and this is m, and this is 1 upon cos, and cos is minus sign, so it will be minus 10 x minus 1, and this is equal to minus 1. Now this minus and minus will cancel. We can write this as limit x tends to 1 positive n x minus 1 to the power n minus 1 upon m 10 x minus 1. Now this limit, it must be equal to 1. Now we know that 10x upon x, it is 1. That means this x minus 1 to the power n minus 1, it should be actually x minus 1 to the power 1. So that means value of n is 2. If value of n is 2, this limit is 1. From here we get n equals m, and since n is 2, therefore m is also 2. So answer to this question is this option C, n equals to n, m equals to. Now here the question is, let Px be a polynomial of degree 4 having extremum at 1 and 2. And it says limit x tends to 0, 1 plus Px upon x square, it is equal to 2. Now if 1 plus Px upon x square is equal to 2, that means minimum power of x in Px, it must be x square and its coefficient must be 1. So it will be this x square, then ax cube plus b x to the power 4. Now if we find p dash x will be 2x plus 3ax square plus 4b x cube. Now p dash 1 is 0 and p dash 2 is 0. Now if we put p dash 1, we get 3a plus 4b and there will be minus 2. And if we put this as 2, we'll get this as 6a plus 16b and there will be minus 2. Now we'll multiply this first with 2 and we'll subtract it. Then it will be 8b and 8b equals to 2. Value of b is 1 by 4. And if we put b as 1 by 4, it will be this 4. Value of a is minus 1. So this function px, it will be x square minus x cube plus 1 by 4 x to the power 4. Now we need to find the value of p2. Now p2 will be 4 minus 8 and plus 4, which is 0. So answer to this question is simply 0. Now question number 1 is, for any polynomial pt, the limit t tends to infinite pt upon e to the power t is independent of polynomial p. Justify the statement and find the value of this limit. So we have this limit, which is limit t tends to infinite p as a function of t upon e to the power t. Now if we put t as infinite, this numerator will be plus or minus infinite and then e to the power infinite will be infinite. So when it is infinity upon infinity form, we can use L'Hopital's rule. And if we use L'Hopital's rule, we can write this as limit t tends to infinite p dash t upon e to the power t. Then again it will be plus minus infinity upon infinity. So we can differentiate it again. We can keep using L'Hopital's rule till we differentiate this function n times, which is degree of this polynomial. And if we differentiate this polynomial up to its degree, then it will be some constant upon infinite, and any constant upon infinite is simply 0. So this statement is true and the value of this limit is simply 0. So that's your part A. Now part B is, show that q dash 0 exists and find its value. And why is it enough to calculate the relevant limit from only one side? Now we'll find q dash 0 positive. Now q dash 0 positive will be limit h tends to 0 q 0 plus h minus q0 upon h. Now this is limit h tends to 0. Now q h positive when x is greater than 0 is simply e to the power minus 1 by h. q0 is 0 and here it will be this h. So we can write this as limit h tends to 0 1 by h and then e to the power 1 by h. Now what we will do is we'll let 1 by h as t, then we can write this as limit t tends to infinite t upon e to the power t, which is of the form pt upon e to the power t, and we know that this limit is equal to 0. So q dash 0 positive is 0. Now we need not calculate q dash 0 negative as this given function is an even function. So suppose we have to find the value of q minus 2 will be e to the power minus 1 by 2, and which is same as value at 2. So this given function is an even function. So we just have to calculate limit from only one side. So this q dash 0 exists and its value is simply 0. Now part C is, for any positive integer n, show that qn0 exists and find its value. Here qx is the function in part B and qn0 denote the nth derivative at x equals 0. Now what we'll do is, for this part C, we have to find nth derivative of this function at 0. Now we know that qx, it is an even function. Now if qx is even, q1x is odd, q2x is even, and continues. So we can say this q&x will be even when n is even, and will be an odd function when n is an odd function. So we can simply write qn minus x will be minus 1 to the power n q nx. Now if we look at this function, which is qx, when x is greater than 0, it is e to the power minus 1 by x. Now q1x will be e to the power minus 1 by x into 1 upon x square. Now we find q2x will be e to the power minus 1 by x minus 2 upon x cube plus 1 upon x square e to the power minus 1 by x, and then 1 by x square, which is e to the power minus 1 by x minus 2 upon x cube plus 1 upon x to the power 4. Now we keep differentiating it. We can write qnx will be of the form e to the power minus 1 by x and then some polynomial expression of 1 by x. Now if we have to find qn0 positive, it will be this limit h tends to 0 e to the power minus 1 by h p1 by h. If we let 1 upon h as t, we can write this as limit t tends to infinite pt upon e to the power t, and this we have already established in part A that this is equal to 0. So from here we can say this qn0 positive will be equal to qn0 negative and will be equal to 0. That is, this qn0 will exist and it is equal to 0. Now question number 9 is, we need to find these limits. Now for this function fx, if we take this limit x tends to 0, x upon x plus sin x, now we can write this as 1 upon 1 plus sin x upon x. Now sin x upon x is 1, so this value is 1 by 2, so this option A is correct. Now if we take this limit x tends to infinite, in that case we can write this as limit x tends to infinite. This is 1 upon 1 plus sin x upon x. Now this is oscillating value minus 1 to 1 upon infinite, so it will be 0. So in this case value of this limit is 1. So this limit, it exists, so this option B is incorrect. If we take this limit x tends to infinite, we can write limit x tends to infinite x to the power 4 plus x to the power 6 upon e to the power x minus 1 minus x square infinity upon infinity form. Now if we keep using L'Hopital's rule, then we can write this as limit x tends to infinite. It will be factorial 6 upon e to the power x. Now e to the power infinite is infinite, so anything finite upon finite will be 0. So this limit x tends to infinite, gx is finite, so this option C is also correct. Now we look at this option D, limit x tends to 0, gx. Now we use L'Hopital's rule in this, we can write limit x tends to 0. Now this is 4x cube plus 6x to the power 5. Now this is e to the power x minus 2x. Now this limit, it is 0. So this option D, it is incorrect. So the correct options are A and C. Now question number 5 is, let A1 be greater than A2 be greater than AR. Then we need to find this limit, which is limit n tends to infinite A1 to the power n plus A2 to the power n plus AR to the power n to the power 1 by n. Now we know that we can write this A1 as A1 to the power n to the power 1 by n, and it will be less than A1 to the power n plus A2 to the power n plus AR to the power n whole to the power 1 by n. Now each of AI, it is always less than A1. So it will be less than R into A1 to the power n to the power 1 by n. So from here we can write A1 is less than A1 to the power n plus A2 to the power n plus AR to the power n to the power 1 by n will be less than R to the power 1 by n into A1. Now we'll take this limit n tends to infinite. Now this limit is A1. This limit is also A1. So from sandwich theorem, we can say that the value of this limit will be simply A1. Now question number 9 is, consider all non-empty subsets of the set 1, 2 up to n. For every such subset, we find the product of reciprocals of each of its element. Denote the sum of all these products as Sn. For example, S3 is 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon 1 into 2 plus 1 into 3, 2 into 3, and then 1 into 2 into 3. Now we can write this S3 as 1 plus 1 upon 1, 1 plus 1 upon 2, 1 plus 1 upon 3, and then minus 1. Now this product, it has all these elements. So we can find sum of all these products Sn as 1 plus 1 upon 1 into 1 plus 1 by 2, 1 plus 1 by 3 up to 1 plus 1 by n minus 1. Now we can also write Sn minus 1 as 1 plus 1 upon 1, 1 plus 1 by 2 up to 1 plus 1 by n minus 1 minus n. Now if in this product we consider all these terms up to 1 plus 1 by n minus 1, then it will be equal to Sn minus 1 plus 1. So you can write this Sn as Sn minus 1 plus 1 into 1 plus 1 by n minus 1. Now if we multiply it, we can write 1 plus 1 by n Sn minus 1 plus 1 plus 1 by n minus 1. Now this 1 and 1 will cancel. So from here we can say this Sn will be equal to 1 by n plus 1 plus 1 by n into Sn minus 1, which is what we need to prove in part A. Now part B is hence or otherwise deduce that Sn, it is equal to n. Now again if we consider this Sn, it is 1 plus 1 upon 1. Next is 2 plus 1 upon 2, 3 plus 1 upon 3, and it will go all the way up to n plus 1 upon n minus 1. Now this is 1, 2, 2, 3, 3, 4, and it goes all the way up to n plus 1 minus 1. Now this 2 will cancel, 3 will cancel, all these terms they'll cancel. We'll get this Sn as n plus 1 minus 1. This 1 and 1 will cancel. So we can write Sn, it is equal to n, which is what we need to prove in this second part. Question number 16 is, consider real valued function f satisfying fx plus 1 equals fx for all x belongs to R. That means this function is periodic with period 1. We are given that gt is this integral from 0 to t
fx dx, and we have defined this function ht as this limit n tends to infinite g t plus n upon n. Now, if we look at gt plus n will be nothing but 0 to t plus n fx dx. Now, we can write this as this integral from 0 to n fx dx plus n to n plus t fx dx. Now, this function is periodic with period 1. So, we can write this as n into this integral from 0 to 1 fx dx, and then plus, now this is from nt to nt plus a, and it will be from 0 to t fx dx. So we can write this function h as this limit n tends to infinite n, this integral from 0 to 1 fx dx plus this integral from 0 to t fx dx upon n. Now we split it in two parts. This n and n will cancel, and 1 upon infinite will be 0. So this ht will be nothing but will be this value from 0 to 1 fx dx, which is a constant function. So this ht, it is defined for all t belongs to R, and it is independent of t, and that's here option C. Question number 24 is, let alpha greater than 0 and consider the sequence xn equals alpha plus 1 to the power n plus alpha minus 1 to the power n upon 2 alpha to the power n. Then limit n tends to infinite xn is. So we have to find this limit n tends to infinite, and xn is alpha plus 1 to the power n plus alpha minus 1 to the power n upon 2 alpha to the power n. Now what we'll do is, we'll consider this limit in two parts. We'll write limit, and if we take this first part, it will be 1 by 2 plus 1 by 2 alpha to the power n plus limit n tends to infinite 1 by 2 minus 1 by 2 alpha to the power n. Now we consider this first limit, which is limit n tends to infinite 1 by 2 plus 1 by 2 alpha to the power n. Now if we take alpha as 1, this value will be simply 1. If we take alpha greater than 1, in that case, this expression will be less than 1. Now a to the power infinite, when a is less than 1, is nothing but 0. And if alpha is less than 1, in that case, this value will be greater than 1, then a to the power infinite will be simply infinite. So this first limit will take the values 1, 0 and infinite depending on the value of alpha. Now for the second limit, which is limit n tends to infinite 1 by 2 minus 1 by 2 alpha to the power n. Now if we take this first case, when 1 by 2 minus 1 by 2 alpha, it lies between minus 1 and 0. Now this value will be minus 3 by 2, it will be less than minus 1 upon 2 alpha, and it will be less than minus 1 by 2, 3, it will be greater than 1 by alpha, and it will be greater than 1. And if we take reciprocal, we'll get alpha is greater than 1 by 3 but less than 1. In that case, this value, it will lie between minus 1 and 0. Then in that case, e to the power infinite will be simply 0. So for this case, value of this limit is simply 0. Now if we take alpha as 1 by 3, we'll get this value is -1. So it will be -1 to the power n. Then this limit, it will oscillate between -1 and +1. And if alpha is less than 1 by 3, then this expression, it will be less than -1. And if it's less than -1, then this limit, it will oscillate between -infinite and +infinite. Now, if we add these two limits, then this limit n tends to infinite xn, it will take this value 0 when alpha is greater than 1, it will be 1 when alpha equals 1, and it will be infinite when alpha is less than 1. So this limit xn will take the value 0, 1 or infinite depending on the values of alpha, and which is your option D.
Now this third question is, we are given that fx plus 1 equals 1 by 2 fx. Now let an equals from 0 to n fx dx. We need to find this limit n tends to infinite an. Now in this equation, if we put x as x plus n minus 1, then we can write fx plus n as 1 by 2 f x plus n minus 1 will be equal to 1 upon 2 square f x plus n minus 2, and using iteration it will eventually come to 1 upon 2 to the power n into fx. Now we need to find this integral an, which is from 0 to n fx dx. Now we need to find this limit n tends to infinite an, which is this summation r varies from 0 to infinite integral from r to r plus 1 fx dx. Now what we'll do is, we'll replace x with t plus r. Then we can write this as this summation r varies from 0 to infinite. Here will be from 0 to 1 ft plus r dt. Now using this relation, we can write f t plus r as 1 upon 2 to the power r into ft. So it will be this summation r varies from 0 to infinite 1 upon 2 to the power r, then this integral from 0 to 1 ft dt. Now this is nothing but an infinite GP. Now sum of this GP will be a upon 1 minus r into this integral from 0 to 1. Now ft dt is same as fx dx. So we can write this as 2 times this integral from 0 to 1 fx dx, and that's your option D. The question is, fx is e to the power minus mod x, and we are given this g theta, which is integral from -1 to 1 f x upon theta, which is e to the power minus mod of x upon theta dx. Now this function, it is an even function, so we can write g theta as 2 times and this integral from 0 to 1 e to the power minus mod x upon mod theta dx. Now when x is greater than 0, mod x is simply x. So it will be 2 times this integral from 0 to 1 e to the power minus x upon mod theta dx. Now if we integrate this function, we can write this as e to the power minus x upon mod theta upon minus 1 upon mod theta, this integral from 0 to 1. So we can write g theta as 2 times mod of theta and then 1 minus e to the power minus x upon mod theta. Now we need to find this limit, which is limit theta tends to 0 g theta upon theta, and there will be this limit theta tends to 0 2 times mod of theta upon theta, and here this value should be 1.
1 minus e to the power minus 1 upon mod theta. Now whether we take this as theta positive or theta negative, it will be e to the power minus infinite, and this will always be 0 for both left hand limit and right hand limit. Whereas this expression, it will be minus 2 in the case of left hand limit, and it will be plus 2 in the case of right hand limit. That means this limit does not exist, and that's your option D. Question number 23 is, we need to find this limit n tends to infinite fractional part of 3 plus 2 root 2 to the power n. Now what we'll do is, we'll say, suppose its integral part is r and fractional part is f, we can write this as 3 plus 2 root 2 to the power n. Now this is nc0 3 to the power n plus nc1 3 to the power n minus 1 2 root 2 and so on, and then we'll consider this f, which is 3 minus 2 root 2 to the power n. It lies between 0 and 1. This capital F, it lies between 0 and 1, and here also any fractional part, it lies between 0 and 1. Now if we add them, we can write r plus f will be 2 times 3 to the power n plus nc2 3 to the power n minus 2 into 2 root 2 square. Now this right hand side, it is integer. This r, it is also an integer. That means this f plus f, it must also be an integer. Now if we add capital F plus small f, it lies between 0 and 2, and the only integral value possible in this case is 1. So we can write this small f as 1 minus capital F, or fractional part of 3 plus 2 root 2 to the power n will be 1 minus 3 minus 2 root 2 to the power n. Now we'll take this limit n tends to infinite. Limit n tends to infinite. Now this is 1, and this value, it lies between 0 and 1. So a to the power infinite in this case will be simply 0. So answer to this limit is 1, and that's your option B. Now here we need to find the value of this limit, which is limit n tends to infinite n plus 1, this integral from 0 to 1, x to the power n, log 1 plus x into dx. Now we'll take this log as first function and this x to the power n as second function. We can write this limit as limit n tends to infinite. Now it will be n plus 1, and here we'll use by parts. So first function as it is, and then it will be x to the power n plus 1 upon n plus 1 minus, now derivative first, so it is 1 upon 1 plus x, and then it will be x to the power n plus 1 upon n plus 1 into dx. Now we'll put the limits. Limits are from 0 to 1. Now here n plus 1 will cancel. So we can write this as limit n tends to infinite. Now we'll put x as 1, it will be log 2 minus 0, and then minus this integral from 0 to 1, x to the power n plus 1 upon x plus 1 into dx. So it will be log 2 minus this limit n tends to infinite from 0 to 1, x to the power n plus 1 upon x plus 1 into dx. Now when n tends to infinite, this x, it lies between 0 and 1. So this value will be nearly 0. So value of this integral is nothing but 0. So answer to this limit will be log 2, and that's your option number B. Now question number 81 is, if f is continuous from 0 to 1, we need to find this limit. Now we see j by n, we know that j by n, it corresponds to x, and 1 by n, it corresponds to dx. So we can change this limit into this integral, which is fx into dx. Now here x is j by n. Now we need to find limits of this function. When j is 0, clearly x is 0. So lower limit is 0. Now what about its upper limit? Its upper limit will be x equals greatest integral function of n by 2 upon n when this limit n tends to infinite. Now we know that greatest integral function of x is x minus fractional part of x. So it will be limit n tends to infinite n by 2 minus fractional part of n by 2 upon n. So it will be 1 by 2 minus this limit n tends to infinite, fractional part of n by 2 upon n. Now fractional part, it always lies between 0 and 1. So anything finite upon infinite is 0. So the value of this limit is 0. So the upper limit of this function will be 1 by 2. So we can write this limit as this integral from 0 to 1 by 2 fx dx, and that's your option number D. Now question number 14 is, let Vn be a sequence defined by V1 which is 1, and then Vn plus 1 equals under root of Vn square plus 1 upon 5 to the power n. Then we need to find this limit n tends to infinite Vn. Now we can write Vn plus 1 square minus Vn square as 1 upon 5 to the power n. Now we'll put n as 1, we'll get V2 square minus V1 square, it is 1 by 5. If we'll put n as 2, we'll get V3 square minus V2 square, it'll be 1 upon 5 square, and then we can write Vn square minus Vn minus 1 square, it'll be 1 upon 5 to the power n minus 1. Now we'll add them. Now we'll add them, all these terms they'll cancel. From here we can write Vn square minus V1 square, and it'll be 1 by 5 plus 1 upon 5 square plus 1 upon 5 to the power n minus 1. So we can write Vn square as, now V1 is 1, 1 plus 1 by 5, 1 by 5 square, 1 upon 5 to the power n minus 1. Now we need to find this limit, limit n tends to infinite Vn. So we'll find limit n tends to infinite Vn square, it is nothing but, it is this infinite GP. So we know that sum of infinite GP is a upon 1 minus r. So from here we can write Vn square limit n tends to infinite, it will be 1 upon 1 minus 1 by 5, which is 5 by 4. So this limit n tends to infinite, Vn will be simply root 5 by 4, and that's your option number B. Now question number 29 is, let psi be a continuous function such that psi y is 0 for all y which doesn't lie between 0 and 1, and this integral from 0 to 1 psi y dy is 1. We need to find this limit, which is limit n tends to infinite n into this integral from 0 to 100 fx into psi nx dx. Now what we'll do is we'll use substitution to make it some y. So we'll take let nx equals y, then dx is nothing but it is 1 upon n dy. So we can write this limit as limit n tends to infinite, and then n dx is dy. So it'll be f y upon n psi y dy, and then this integral from 0, and then when x is 100 it will be simply 100n. Now we can write this as limit n tends to infinite from 0 to 1 f y by n psi y dy plus limit n tends to infinite from 1 to 100n f y by n psi y dy. Now when y doesn't lie between 0 and 1, psi y is 0. So this function is 0. So this limit will simply be 0. Now we can write this limit as from 0 to 1 limit n tends to infinite f y by n and then psi y dy. Now when n tends to infinite, 1 upon n is 0. So it will be simply from 0 to 1 f0 psi y dy. We can take this f0 out, and then what is integral of psi y dy? It is nothing but 1. So answer to this limit is f0, and that's your option number A. Question number 7 is, let x naught greater than 0 and xn be defined recursively by xn equals under root of 6 plus xn minus 1, where n is greater than or equal to 1, then this limit n tends to infinite xn is. Now we can write this xn as under root of 6 plus xn minus 1. We can write this as xn square, it will be 6 plus xn minus 1. Now what we'll do is we'll subtract xn minus 1 square from it. So it will be xn square minus xn minus 1 whole square, and if we take minus common here, we'll get xn minus 1 square minus xn minus 1 minus 6, and if we factorize it, we can write this as xn minus 1 minus 3 and xn minus 1 plus 2. Now here critical points are 3n minus 2, and since x0 is greater than 0, we'll take two cases. Case 1, if x0 is less than 3, and case 2 if x0 is greater than 3. Now if x0 is less than 3, then if we add 6, we'll write 6 plus x0 will be less than 9, that is under root of 6 plus x0 will be less than 3. We can write x1 will be less than 3, and using same iteration we can write xn will be less than 3. Then in that case this function will be bounded above. Now if xn is less than 3, then this value will be negative, this value will be positive, and then we have this minus sign here, so it will be minus and minus plus. So we can write xn square minus xn minus 1 square, and it will be greater than 0, that is xn is greater than xn minus 1, that is the sequence is monotonic increasing. So if the sequence is bounded above and increasing, that means this sequence it is going to converge. Now what about the second case? And the second case, when x0 is greater than 3, if we add 6, we'll get 6 plus x0 will be greater than 9 under root of 6 plus x0 will be greater than 3, that is x1 is greater than 3. If we add 6, again if we take square root, we'll get x2 greater than 3. So from here we'll get this xn, it should be greater than 3. So in this case it is bounded below. Now if xn is greater than 3, then this expression will be positive, this is also positive, and here we have this minus sign. So we'll get xn square minus xn minus 1 square, it should be less than 0, that is xn, it should be less than xn minus 1. That means this sequence is now a decreasing sequence. So if the sequence is bounded below and monotonic decreasing, that means this sequence it will converge. Now what about if x0 is 3? If x0 is 3, then this sequence will be a constant sequence, and we know that a constant sequence is a convergent sequence. So this sequence will be convergent for all the possible values of x0. Now we'll need to find this limit n tends to infinite xn. For that what we'll do is we'll take this limit n tends to infinite both sides. Now suppose this limit is L. So we can write L equals under root of 6 plus L, that is L square minus L minus 6 equals 0. That is the value of L is either 3 or the value of L is minus 2. Now since this sequence it contains positive terms, its limit point cannot be negative. So for this sequence, the value of this limit is simply 3. So this limit n tends to infinite xn will be 3, and which is none of the above, option D. Question number 5a is we need to find this limit. So we'll take log both sides. We can write log a as this limit n tends to infinite. Now this power will come out, so it will be 1 by n, and then log sine pi upon 2n into sine 2 pi upon 2n up to sine n pi upon 2n. Now we know that log m into n is log m plus log n. So we can write this as log a, and it will be equal to this limit n tends to infinite 1 by n, and we can write this as summation log sine pi r upon 2n, where the value of r varies from 1 to n. Now this is nothing but limit of sum. So we can write this as log a equals to limit n tends to infinite. Now we'll change this summation into this integral form. It will be log, now sine pi by 2 r upon n. We'll take r upon n as x, so it will be log sine pi upon 2x into dx. Now what are the limits? Lower limit is when the value of r is 1, so it will be 0, and upper limit is 1. So value of this limit will be this integral. So we can write log a as this integral from 0 to 1 log sine pi by 2x into dx. Now what we'll also do is we'll let pi by 2 into x as some t. So we can write log a. Now here will be log sine t, and then derivative of dx will be 2 upon pi dt. So it will be 2 upon pi dt, and this limit will change from 0 to pi by 2. So we can write log a equals 2 upon pi, this integral from 0 to pi by 2 log sine t dt. Now this is standard integral. We know that value of this integral is minus pi by 2 log 2. So here pi and pi will cancel, 2 and 2 will also cancel. So we can write log a equals minus log 2, that is the value of a is simply 1 by 2. So answer to this question is the value of this limit is simply 1 by 2. Now question number 6a is we are given this function fx, which is the summation n varies from 0 to infinite x to the power n factorial n to n minus 1 by 2. We need to find the value of this limit, which is limit x tends to 0 fx minus e to the power x upon 1 minus cos x. Now if we'll write the series, we can write the series of fx as when n is 0, this is x to the power 0, which is 1, factorial 0 is 1, and 2 to the power 0 is 1, so it will be 1 plus. Now we'll take n as 1, it will be x, and then here it will be 1, and then 2 to the power 0 is 1, so it will be x upon 1 plus, for n equals 2, it will be x square, and here it will be factorial 2 and 2 to the power 1, so it will be x square upon 4 plus, we'll use this big O notation, x cube. In the same way, we can write expansion of e to the power x, it will be 1 plus x square upon 2 plus ox cube, and for cos x, it will be 1 minus x square upon factorial 2 plus o x to the power 4. Now we'll find this limit. So this limit is limit x tends to 0. Now for fx, we'll write 1 plus x square by 4, and for e to the power x, it will be 1 plus x square by 2, and then ox cube, and here 1 minus cos x will be 1 minus x square upon 2 plus o x4. Now here 1 plus x will cancel, and in the denominator 1 and 1 will cancel. We'll write limit x tends to 0. Now this is x to the power 4. Now this is x square upon 4 minus x square upon 2, so it will be minus x square upon 4 plus other higher powers of x, and here it will be x square upon 2 and other higher powers of x. Now this is limit x tends to 0. So lowest power in the numerator is same as lowest power in the denominator. So answer to this limit will be simply minus 1 by 4 upon 1 by 2, which is minus 1 by 2. So value of this limit is minus 1 by 2. Question number 8b is we are given a sequence in which a0 is 1 and a1 is 1, and for n from 1, 2, 3, 4, it defines an plus 1 as 1 plus an minus 1 square by 4. Now the question is, does the sequence an converge to a finite limit as n tends to infinite? And if it does, we need to find this limit. In the first part, we'll prove that this an plus 1, it is bounded. So we'll show that an plus 1 will lie between 0 and 1, and we'll prove this by induction. So our statement is, for any n greater than or equal to 1, an plus 1, it is greater than 0 but less than 1. Now we'll put P1. Now P1 is actually A2. Now what's A2? A2 is 1 plus A1. A1 is 1. A0 square. A0 is also 1. So divide by 4. So it is 3 by 4. So value of A2 lies between 0 and 1. Now we'll assume that it will be true for any value of k starting from 1 to n. So we can write ak minus 1 will lie between 0 and 1, and ak will also lie between 0 and 1. Now we'll need to prove that this statement is true for k plus 1. So for k plus 1, we can write ak plus 1 as 1 plus ak minus 1 square upon 4. Now we know that ak lies between 0 and 1. ak minus 1 also lies between 0 and 1. Now we'll square it. We'll write 0, and then ak minus square will also lie between 0 and 1. So we'll add them. We can write 0 and ak plus ak minus 1 square will lie between 0 and 2. Now we'll add 1. So we'll add 1. We can write 1 is less than 1 plus ak minus 1 square, and it is less than 3. Now we'll divide it with 4. This is nothing but ak plus 1. So from here we can say this ak plus 1 will be greater than 0 but less than 1. So from induction we have proved that any term for the sequence will always lie between 0 and 1. Now we need to find the limiting value of the sequence. So what we'll do is, here we'll take limit n tends to infinite. So it'll be limit n tends to infinite, and it'll be equal to this limit n tends to infinite 1 plus an minus 1 square upon 4. Now suppose this limit exists and it is equal to L. So this is L, and here it will be 1 plus. Now again, when n tends to infinite, this is limiting value of this sequence. So it will be again L, and here it will be L square by 4. So from here we'll get this condition, which is L square minus 3L plus 1 equals 0. Now it is a quadratic equation in L. So we'll solve this equation. We'll get L as 3 plus minus under root of 9 minus 4 by 2. So limiting value of the sequence will be 3 plus minus under root 5 by 2. Now in the first part, we have already proved that this ak plus 1 should be less than 1. So the only value possible in this case is 3 minus root 5 by 2. So the sequence, it converges to a finite limit, and that finite limit is 3 minus under root 5 by 2, and that is the answer to this question. Now question number 10 is, we need to find the value of this infinite product, which is 7 upon 9 into 26 upon 28 into 63 upon 65, and it is of the form n cube minus 1 upon n cube plus 1. So we can write this P as this product n cube minus 1 upon n cube plus 1, where the value of n varies from 2 to infinite. Now we can write this as this product, and this is a minus b, a square plus ab plus b square, and here it will be n plus 1, n square minus n plus 1. So what we'll do is we'll split this product in two parts. So first one will be n varies from 2 to infinite, n minus 1 upon n plus 1, and then this product, which is n varies from 2 to infinite, n square plus n plus 1 upon n square minus n plus 1. Now in the first product, if we'll put the value of n as 2, we'll get 1 upon 3, and then it'll be 2 upon 4, 3 upon 5, 4 upon 6, will continue. And the same way here we'll get 4 plus 2, 6, and this is 7. And this is 4 minus 2, 2 plus 1, 3. Now we'll put n as 3, it'll be 9, 10, 13. And here will be 9 minus 3, 6 plus 1, 7. And this series again will continue up to infinite. Now here this 3, 4, 5, 6, they'll all get cancelled. And here also this 7, 13 will get cancelled. So we'll get this result as simply 2 by 3. So value of this infinite product will be 2 by 3, and that's your option number B. Now question number 19 is we'll need to find this limit, which is limit n tends to infinite. Then summation k varies from 1 to n, and this is e to the power 2 pi by n into iota k minus e to the power 2 pi iota k minus 1 upon n. Now for the sake of brevity, we'll write 2 pi by n as some theta. So we can write this as summation e to the power iota k theta minus e to the power iota k minus 1 theta. And this summation, it varies from 1 to n, where limit n tends to infinite. Now here we'll take e to the power iota k minus 1 theta common. So we'll take it common. We can write limit n tends to infinite summation k varies from 1 to n, and then mod of e to the power iota k minus 1 theta, and then e to the power iota theta minus 1. Now modulus of e to the power iota theta is simply 1. So this value will be 1. So we can write this as limit n tends to infinite, and then summation k varies from 1 to n mod of e to the power iota theta minus 1. Now this expression, it is independent of k. So it will actually be limit n tends to infinite n into mod of e to the power iota theta minus 1. Now we'll put the value of theta. Theta is 2 pi by n. So we can write this limit as limit n tends to infinite e to the power 2 pi by n iota minus 1, and this mod upon 1 by n. Now we'll multiply and divide it with mod of 2 pi iota. So this limit, it is standard limit e to the power x minus 1 upon x, which is 1. And then mod of 2 pi iota is simply 2 pi. So answer to this limit is simply 2 pi, and that's your option number C. Now question number 22 is we are given this an, which is 1 minus 1 upon root 2, 1 minus 1 upon root 3 up to 1 minus 1 upon root n plus 1. We need to find this limit n tends to infinite an. Now we know that one minus 1 upon root 2 is less than 1 upon 1 minus root 3 is less than 1 upon 1 minus root 4, and will be less than 1 upon 1 minus under root of n plus 1. Now we know that all the terms, they are greater than 1 minus 1 upon root 2. So if we'll replace all the terms in the product with 1 minus 1 upon root 2, we can say that an is always greater than 1 minus 1 upon root 2 to the power n. It will always be less than its maximum value. Maximum value is 1 minus 1 upon under root n plus 1, and then again n times. Now we'll take this limit, which is limit n tends to infinite. Now this expression, it is less than 1. Now when a is less than 1, then a to the power infinite is simply 0. Now what about this right hand limit? This right hand side limit, it is of the form 1 to the power infinite. So again we'll use shortcut. So it'll be e to the power limit n tends to infinite, and then n, and fx minus 1 will be under root of n plus 1. So this value, it will be e to the power minus infinite, which again is 0. So this limit on the left, it is 0, and this limit on the right is also 0. Then from sandwich theorem, we can say that this limit n tends to infinite an, it will be 0, and that's your option number D. Now question number 18, it says let p and b number of digits when 8 to the power n is written in base 6 and let Qn be number of digits when 6 to the power n is written in base 4. We need to find this limit, which is limit n tends to infinite Pn Qn upon n square. Now there is a direct formula for that. So if we write 8 to the power n to the base of 6, then number of digits Pn, it is given by greatest integer function of log 8 to the power n to the base 6 and then plus 1. So this is the formula to find out number of digits in other base. So in the same way, we can find number of digits Qn when the base is 4. So Qn will be log base is 4 and number here is 6 to the power n and plus 1. So basically Pn is n log 8 base 6 plus 1 and Qn is greatest integer n log 6 base 4 plus 1. Now we need to find this limit, which is limit n tends to infinite Pn into Qn upon n square. Now in greatest integer function, we know this property that greatest integer function of x is always less than or equal to x and it is greater than x minus 1. So I can write Pn is less than or equal to n log 8 base 6 plus 1 and it is greater than n log 8 base 6. In the same way, we can write Qn. So Qn will be less than n log 6 base 4 plus 1 and here will be n log 6 base 4. Now if we multiply them, then we can write it as n square log 8 base 6 into log 6 base 4 is less than Pn into Qn and it is less than n log 8 base 6 plus 1 into n log 6 base 4 plus 1. So now I'll need to find this limit. So I'll need to divide it with n square. So I'll also divide it with n square. So if I'll divide it with n square and I'll take this limit also. I'll take this limit n tends to infinite. Now since it is an infinite limit, so highest power of n in the numerator and denominator is 2. So answer to this left hand limit will be simply log 8 into log 6 and here it is limit n tends to infinite Pn Qn by n square, and here also the highest power is n square. So here also this limit will be log 8 base 6 into log 6 base 4. Now Sandwich's theorem says if fx lies between gx and hx and if limiting value of gx is L and limiting value of hx is L, then the limiting value of this limit is also L. So which simply means the value of this limit is equal to log 8 base 6 into log 6 base 4. So I can write it as log 2 base 8 upon log 6 base 2 and here will be log 6 base 2 upon log 4 base 2. So it will cancel. So 8 is 2 cube and 4 is 2 square. So the value of this limit is simply 3 by 2 and that's your option number C. Now question number 20 is this function from R to R be a non-zero function such that this limit x tends to infinite fxy upon x cube exists for all y greater than 0. Let gy equals this limit x tends to infinite fxy upon x cube. Now it is given that g1 is 1. So we'll put y as 1. We can write limit x tends to infinite fx upon x cube, it is equal to 1. Now we'll need to find gy. Now what we'll do is we'll write this gy as this limit x tends to infinite fxy, and here we'll write this as xy cube into y cube. Now we can write this gy as y cube into limit x tends to infinite fxy upon xy cube. Now when x tends to infinite, xy also tends to infinite, so this limit, its value is 1. So we can write this function gy, it must be this function y cube, and that's your option D. Now question number 27 is, for alpha belongs to 0 to 3 by 2, define xn as n plus 1 to the power alpha minus n to the power alpha. We need to find this limit n tends to infinite xn. Now if the value of alpha is 1, then clearly in that case xn will be n plus 1 minus n, which is 1, and if we'll take this limit n tends to infinite, simply it'll be 1. Now when alpha is not equal to 1, then in that case we can write this xn as n to the power alpha 1 plus 1 upon n to the power alpha minus 1. We can write this as 1 plus alpha upon n, alpha minus 1 upon factorial 2, 1 upon n square, and then minus 1. Now this 1 and 1 will cancel. So we can write this as limit n tends to infinite xn, and it will be limit n tends to infinite alpha into n to the power alpha minus 1 plus alpha minus 1 upon factorial 2 n to the power alpha minus 2. Now if alpha lies between 0 and 1, all these powers of n, they'll be simply 0. In that case, the value of this limit, it will be simply 0. But if alpha lies between 1 and 3 by 2, then this n, it will have a positive power, and when it'll have a positive power, then this xn will approach infinite. So answer to this limit will be 1, 0 or infinity, depending on the value of alpha, and that's your option D. Now question number 30 is, we are given this function from 0 to 1 to minus 1 to 1, and it'll be a non-zero function such that f2x is equal to 3fx when x lies between 0 and 1 by 2. We need to find this limit x tends to 0 positive fx. Now what we'll do is, we can write this fx as 1 by 3 f2x. Now we can write f2x as 1 upon 3 square into f 2 square x, and if we continue the iteration, we can write this as 1 upon 3 to the power n f 2 to the power of n into x. Now we can keep doing it till we get this limit n tends to infinite. So we can write this function fx as this limit n tends to infinite f 2 to the power of n into x upon 3 to the power of n. Now we need to find this limit x tends to 0 positive fx, and it'll be equal to this limit x tends to 0 positive limit n tends to infinite f 2 to the power nx upon 3 to the power n. Now range of this function is from minus 1 to 1. So this value in the numerator will lie somewhere between minus 1 and plus 1, which is a finite value, upon 3 to the power infinite, which is infinite. So value of this limit is 0. So value of this limit x tends to 0 fx is equal to 0, and that's your option D. Now the question is, we are given this function f defined from minus pi by 2 to plus pi by 2, and f0 is 1, and this integral from 0 to pi by 3 ft dt, it is 0. Now which of the following options is or are correct? Now what we'll do is, we'll assume a function gx, which is this integral from 0 to x ft dt minus sine 3t in the interval x belongs to 0 and pi by 3. Now if we find g0, it is 0 and sine 0 is also 0. So value of g0 is 0, and if we find g pi by 3, this integral from 0 to pi by 3, it is 0, and then sine pi will also be 0. So this function gx, it is continuous differentiable. G0, it is equal to g pi by 3. That means this function gx, it satisfies the condition for Rowley's theorem. Then from Rowley's theorem, we can say there exists at least one c in the interval 0 to pi by 3 such that g dash c is 0. Now if we differentiate this, then we can write this is fc minus 3 cos 3c equals 0. So this equation fx equals 3 cos 3x will have at least one solution in 0 to pi by 3. That means this option A, it is correct. Now for this option B, again we'll assume a function and let this function be hx, which is this integral from 0 to x ft dt plus cos 3t plus 6x upon pi in the interval 0 to pi by 3. Now this function again is continuous and differentiable. Now if we find h0, h0 will be cos 0 is 1, and h pi by 3, this integral will be 0. Now cos pi is minus 1 and this value will be 2. So value of h pi by 3 is 1. So again this function hx, it satisfies all the three conditions of Rowley's theorem. So again from Rowley's theorem we can say there exists at least one c in the interval 0 to pi by 3 such that h dash c is 0. Now if we differentiate this function, we can write fc minus 3 sine 3c plus 6 upon pi will be 0. So this equation fx minus 3 sine 3x equals minus 6 upon pi has at least one solution in 0, 3, which means this option B is also correct. Now if we look at this option C, which is this limit x tends to 0, x into this integral from 0 to x ft dt upon 1 minus e to the power x square. Now what we'll do is we'll multiply and divide it with x square. Now we can rearrange this limit as limit x tends to 0, this integral from 0 to x ft dt upon, now x and x will cancel, so it will be this x into, now this is standard limit, e to the power x minus 1 upon x, it is 1, and here it is 1 minus e to the power x square, so this value will be simply minus 1. Now this is 0 upon 0 form. If we use L'Hopital's rule, we can write limit x tends to 0 fx upon 1 and this minus, which is equal to minus f0, and the value of f0 is 1. So value of this limit is minus 1, which means this option C is also correct. Now if we look at this option D, then for this option D we can write limit x tends to 0. Now this is sin x upon x and then this integral from 0 to x ft dt upon x. Now this is standard limit 1 and this is 0 upon 0 form. So again if we use L'Hopital's rule, it will be f0 and f0 is 1. So this value is actually 1 and not minus 1. So option D is incorrect. So the correct options are A, B and C. Now here the question is, let a1 equals 1 and an equals n into an minus 1 plus 1 for n equals 2, 3, 4. Define Pn as 1 plus 1 upon a1 into 1 plus 1 upon a2 up to 1 plus 1 upon an. Then we need to find this limit n tends to infinite Pn. Now we can write this Pn as a1 plus 1 upon a1, a2 plus 1 upon a2, and in the same way it goes up to an plus 1 upon an. Now from this recurring relation we can say that an minus 1 plus 1 upon an, it is equal to 1 upon n. So we can write this as 1 upon a1 and then a1 plus 1 upon a2 into a2 plus 1 upon a3, and it goes all the way up to an minus 1 plus 1 upon an into an plus 1. Now this is 1 by 2, this is 1 by 3, and this is 1 by n. So we can write this as 1 upon factorial n an plus 1 upon a1. Now we are also given that a1 is 1. So we can write this as 1 plus an upon factorial n. Now this is 1 upon factorial n plus an upon factorial n. Now an upon n is an minus 1 plus 1. So we can write an upon n is 1 plus an minus 1. So we can also write this as 1 upon factorial n plus, and this is 1 plus an minus 1 upon factorial n minus 1, which is 1 upon factorial n plus 1 upon factorial n minus 1. Now if we continue in the same fashion, in the end we'll get 1 upon factorial n plus 1 upon factorial n minus 1 plus a2 upon factorial 2. We can also write this as 1 upon factorial n plus 1 upon factorial n minus 1, 1 upon factorial 2 plus, now a2 upon 2 is 1 plus a1, and a1 is 1. So it will be 1 plus 1 upon 1. So that's your Pn. Now we take this limit n tends to infinite Pn, it will be 1 plus 1 upon factorial 1 plus 1 upon factorial 2, and the series, it goes all the way up to infinite. It is nothing but e. So the value of this limit n tends to infinite Pn will be simply e, and that's your option B. Now there are two very important and simple theorems in limits, which are Cauchy theorems on limits. Now the first theorem says, if limit an equals to a and bn is average of all these ai's, then limit of b is same as limit of a. And the second theorem says, if an is a positive number, then for all n, this limit n tends to infinite an to the power 1 by n will be same as this limit n tends to infinite an plus 1 upon an. Now we generally use these theorems to simplify problems in limits. Let us take up an example. Say for example, the question is, show that this limit n tends to infinite 1 upon under root n square plus 1 plus 1 upon under root n square plus 2 up to 1 upon under root n square plus n, and this is equal to 1. Now generally we solve this question using sandwich theorem or squeeze play theorem. Now here we are going to solve this question using Cauchy's theorem on limits. So what we'll do is we'll write this as limit n tends to infinite 1 by n upon under root of n square plus 1 plus n upon under root of n square plus 2 up to n upon under root of n square plus n. Now this limit is of the form limit n tends to infinite 1 by n a1 plus a2 plus an. Now Cauchy's first theorem says this limit, it is equal to this limit n tends to infinite an. So all we need to do is we need to solve this limit n tends to infinite. Now what's an? An is n upon under root of n square plus n, and this limit is nothing but 1. So value of this limit is simply 1. Now here the question is, we need to show that this limit 1 by n, 1 plus 2 to the power 1 by 2, 3 to the power 1 by 3 plus n to the power 1 by n is equal to 1. Now using Cauchy's theorem, we can say that this limit, which is 1 by n a1 plus a2 plus a3 plus an, is equal to limit n tends to infinite an, and an in this case is n to the power 1 by n. Now we can write this as limit n tends to infinite e to the power log n to the power 1 by n. So it will be e to the power this limit n tends to infinite log n by n. Now this is log infinite upon infinite, so it is infinity upon infinity form. We can use L'Hopital's rule. We can write e to the power this limit n tends to infinite, and it will be 1 by n upon 1. So it will be simply e to the power 0, which is 1. So the value of this limit is nothing but 1. Now here the question is, evaluate this limit. Now we'll take this as y, and if we take log, we can write log y equals limit n tends to infinite 1 by n log 2 upon 1 plus log 3 upon 2 square plus log n plus 1 upon n whole to the power n. Now we'll use Cauchy's first theorem. We can write log y equals this limit n tends to infinite an, and an in this case is log n plus 1 upon n whole to the power n. Now this is log y, and it'll be this log, and this is standard limit 1 plus 1 by n to the power n when n tends to infinite, and this is nothing but e. Log e is 1. If we take anti-log, value of y is simply e. So value of this limit is nothing but e. And the second theorem says, if an is a positive number, then for all n, this limit n tends to infinite an to the power 1 by n will be same as this limit n tends to infinite an plus 1 upon an. Now here in this question, we need to find limit of the sequences an to the power 1 by n and bn to the power 1 by n. Now Cauchy's second theorem says this limit n tends to infinite an to the power 1 by n is same as limit n tends to infinite an plus 1 upon an. So for this first one, if we have to calculate this limit will be equal to limit n tends to infinite an plus 1 upon an. Now limit n tends to infinite, what's an plus 1? An plus 1 will be factorial 3n plus 3 upon factorial n plus 1 cube upon an, and an is factorial 3n, and here will be factorial n cube. Now we can write this as limit n tends to infinite. Now it will be 3n plus 3 into 3n plus 2, 3n plus 1. Now factorial 3n will cancel upon n plus 1 whole cube. Now this is infinite limit. Highest power of n is 3. In the numerator is 27 and the denominator it is 1. So value of this limit will be simply 27. So answer to this first one is 27. Now again for the second one, we can write this as limit n tends to infinite bn plus 1 upon bn, and LB this limit n tends to infinite. Now bn plus 1 is n plus 1 to the power n plus 1 upon n plus 2 n plus 3 up to 2n plus 1 2n plus 2 divided by bn, and bn is n to the power n upon n plus 1 n plus 2 up to 2n. Now n plus 2, n plus 3 up to 2n will cancel. Now we can write this as this limit n tends to infinite n plus 1 to the power n plus 2 upon n to the power n 2n plus 1 and 2 into n plus 1. We'll cancel this n plus 1 once. So you'll get n plus 1 to the power n plus 1. Now we can also write this as limit n tends to infinite n plus 1 upon 2n plus 1 into 1 plus 1 upon n to the power n. And we also have this 2 here. Now we take this limit. This part will be simply 1 by 4, and then this is 1 to the power infinite form, and this is standard limit. Its value is e. So limit of the sequence will be simply e by 4. The question is, let Vn be a sequence defined by V1 equals 1 and Vn plus 1 equals Vn square plus 1 by 5 to the power n whole root. Then we need to find limit n tends to infinite Vn. Now we can write this expression as Vn plus 1 square minus Vn square, and it will be equal to 1 by 5 to the power n, and will be greater than 0. From here we can write Vn plus 1 will be greater than Vn, that is, this sequence is monotonic increasing sequence. Now we can write V2 square minus V1 square will be 1 by 5. V3 square minus V2 square is 1 upon 5 square, and then Vn square Vn minus 1 square will be 1 upon 5 to the power n minus 1. Now we'll add everything. We can write Vn square minus V1 square, which is 1, and it'll be 1 by 5 plus 1 by 5 square up to 1 upon 5 to the power n minus 1, that is Vn square is 1 plus 1 by 5 up to 1 upon 5 to the power n minus 1. Now this is nothing but a GP whose sum is a into 1 minus r to the power n upon 1 minus r, which is 1 minus 1 by 5. Now we take this limit n tends to infinite. This value will be 0. So this value will be simply 5 by 4. So limit n tends to infinite. Vn square is 5 by 4. Then this limit n tends to infinite Vn will be simply under root 5 by 4, and that's your option B.
Now the fifth property is, if h is very small number, which is nearly 0, a small positive number, then fractional part of h, because this value will lie between 0 and 1, so this value will simply be h. And if it is fractional part of minus h, then it will be 1 minus h. So we use this property when we solve questions in limits. Say for example, suppose I have this question which is limit x tends to 0 sine fractional part of x upon fractional part of x. Now because I know it's a fractional part function and fractional part function is discontinuous at 0, so I need to take left hand limit and right hand limit separately. So I'll write left hand limit and I'll also write right hand limit. So if I write left hand limit, I'll write limit x tends to 0 negative sine fractional part of x upon fractional part of x. So what I'll do is I'll let x as 0 minus h. So I can write limit h tends to 0 positive, and this is sine fraction part of minus h upon fraction part of minus h. Now what I know is when h is a small positive number, then fraction part of minus h is simply 1 minus h. So I'll write it as limit h tends to 0 positive. So this is sine 1 minus h upon 1 minus h. So if I'll put the value of this h, I'll get this as what? I'll get this as sine 1 upon 1, and which is not an indeterminate form. So the value of left hand limit simply will be sine 1. Now what about right hand limit? Now in case of right hand limit, I'll write it as limit x tends to 0 positive sine fractional part of x upon fractional part of x. So I'll write let x equals 0 plus h. So there will be limit h tends to 0 positive sine fractional part of h upon fractional part of h. Now when h is small positive number, fractional part of h is simply h. So I'll write it as limit h tends to 0 positive, so which is sine h upon h. So if I'll put the value, I'll get this as 0 upon 0, which is indeterminate form. So now it becomes standard limit. So value of right hand limit is simply 1. Left hand limit is sine 1 and right hand limit is 1. So left hand limit is not equal to right hand limit. Therefore, limit does not exist. Limit x tends to 0, greatest linear function of 2 sin x plus tan x upon x, where this box represents greatest linear function. Now in this case also, sin x upon x is 1, tan x upon x is 1, which is 3. Now 3 is an integral point. So at integral point, greatest linear function is discontinuous. So I cannot take this limit inside. So I need to solve it separately. So what I'll do is I'll write it as 2 sin x plus tan x upon x. So I'll use expansion formula. So I'll write the expansion formula for sin x. So it will be 2x minus x cube upon factorial 3, x to the power 5 upon factorial 5, and then plus, and then 10x is x plus x cube upon 3 plus 2 by 15 x to the power 5 whole divided by x. Now here 2x plus x will be simply 3x, and then 2x cube by factorial 3 it will be x cube by 3 and plus x cube by 3, so we'll cancel, and then I'll get this as 2 by factorial 5 plus 2 by 15 x to the power 5 whole divided by x. So if I divide by x, I'll write 3 plus 2 upon factorial 5 plus 2 by 15 x to the power 4. Now this x to the power 4 and this expression, it is a positive coefficient with a positive power. So this value will be positive, and all the remaining power, as the power increases, the value of this x to the power n, it decreases. So this expression will be 3 point something, some positive value. So in that case, if I take its greatest linear function, so greatest linear function of 2 sin x plus tan x upon x, when x tends to 0, it will be simply 3. Now the fifth property of greatest integer function is the value of greatest integer function of x will lie between x minus 1 and x. We know that any x is greatest integer function of x plus f, and this f, it belongs to 0 and 1. So it is greatest integer function of x plus some value. So its maximum value will be simply x, and x minus 1 will always be less than greatest integer function value. Now we use this property while solving limits. Say for example, we have this question which is limit n tends to infinite, greatest integer function of 1 square x plus 2 square x up to n square x divided by n cube. So what we know is, because this n tends to infinite, it is infinity upon infinity form. Now any greatest integer function of x, it will lie between x minus 1 and x. So I can write 1 square x will lie between 1 square x minus 1 and 1 square x. In the same way, 2 square x will lie between 2 square x and 2 square x minus 1. 3 square x will lie between 3 square x and 3 square x minus 1, and this series will continue up to n, that is n square x minus 1, get a function of n square x, and this is n square x. If I add them all up, I can write it as 1 square plus 2 square, it goes up to n square into x, and then minus 1 minus 1 minus 1 n times, so there will be minus n, and this is less than greatest function of 1 square x, get a function of 2 square x, get a function of n square x, and it will be less than or equal to 1 square plus 2 square
up to n square into x. Now for this limit, I'll need to divide it with n cubed. So I'll divide each of the three expressions with n cubed. And I'll also take this limit n tends to infinite for all the three expressions. Limit n tends to infinite. Here also I'll take limit n tends to infinite. And here also I'll take limit n tends to infinite. Now 1 square, 2 square up to n square. This is nothing but limit n tends to infinite. This is n plus 1 to n plus 1 by 6 into x, and then minus n whole divided by n cube. Here it will be simply, so I'm not going to solve this limit. So I'll simply write it as 1 square x up to n square x upon n cube, and this is again n plus 1 to n plus 1 by 6n cube into x, and this is limit n tends to infinite. Now it's an infinite limit. Now in infinite limit, if the degree of numerator and denominator is same, so the degree of numerator is 3 and the degree of denominator is also 3. So answer to this limit simply will be the leading coefficient of n cube in the numerator, which is 2 by 6 x, and leading coefficient of n cube in the denominator, which is 1. And in this case also, it is a polynomial of degree 3 in the numerator, and here also degree in the denominator of n is 3. So again in this case it will be 2 by 6, which is 1 by 3 x. Both these limits on the left hand side and also on the right hand side, the value of both the limits is 1 by 3 x. Sandwich theorem or squeeze play theorem says, if we have a function fx which lies between f1x and f2x, and if I take limit x tends to a, f1x if the value of this limit is L and the value of second limit is also L, then in that case the limit of this function x tends to a fx will also be L. So from sandwich theorem we can say that the value of this limit will also be 1 by 3 x. We use this property while solving the problems in limits. Now question number 5 is, we are given this polynomial px, which is x to the power 20 plus ai x to the power I for all i's from 0 to 19. So we can write this polynomial px as x to the power 20 plus a19 x to the power 19, a18 x to the power 18 plus a1x plus a0. Now it says, if p of x equals p of minus x for all x belongs to R, that means its odd coefficients, they must be 0. So a2n plus 1, they'll be 0. Then in that case, we can write this polynomial px as x to the power 20 plus a18 x to the power 18, a16 x to the power 16 up to a2 x square plus a0. Now we are given that pk equals k square for k equals 0, 1, 2 up to 9. Now what we'll do is we'll consider this equation, which is px minus x square equals 0. Now this equation has 10 real roots, namely 0, 1, 2 up to 9. Now since px is a polynomial with even powers and power of x square is also even, that means if alpha is the root of this equation, then minus alpha will also be the root of this equation. So the roots of this equation must be plus minus 0, plus minus 1, plus minus 2n, plus minus 9. Now degree of this equation is 20, and now we have 20 roots of this equation. So we can write px minus x square as x square into x square minus 1 square, x square minus 2 square up to x square minus 9 square. Now we need to find this limit x tends to 0, px upon sine square x. Now if we divide everything with sine square x, we can write px upon sine square x minus x square upon sine square x LB x square upon sine square x square minus 1 square into x square minus 2 square up to x square minus 9 square. Now we take this limit x tends to 0, then we can write this as limit x tends to 0 px upon sine square x minus this limit is 1. Now this limit is also 1, and if we put x as 0, we'll get this as minus 1 square into minus 2 square up to minus 9 square. So minus 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 9 times will be minus, and then 1 square into 2 square into 9 square. So it will be 1 into 2 into 3 up to 9 whole square, which is factorial 9 square. So value of this limit x tends to 0 px upon sine square x LB 1 minus factorial 9 whole square, and that is the answer to this question. Question number 11, we are given the sequence which is fn x equals x to the power n cos 2 pi nx when x belongs to minus 1 and plus 1. And we need to find this limit n tends to infinite fnx. Now if we consider this first case, when the value of x is 1, we can write fn1 as 1 into cos 2n pi, and cos 2n pi is 1. So in this case, limit n tends to infinite fnx will be simply 1. So for x equal to 1, this limit exists. Now we'll consider the second case when the value of x is minus 1. Now we'll have fn minus 1 and it'll be minus 1 to the power n cos 2n pi into minus 1, which is minus 1 to the power n. Now we take this limit n tends to infinite fnx, then in that case this value, it can be either minus 1 or plus 1, that is we'll get an oscillating value. So in this case, this limit, it does not exist. And finally, when x lies between minus 1 and plus 1, in that case this mod xn cos 2n pi x will be mod of x to the power n into mod of cos 2n pi x, and if we take this limit n tends to infinite, now this is oscillating value from 0 to 1, and since mod x, it lies between 0 and 1, this is 0. Now 0 into anything finite is simply 0. In this case also, this limit exists. So this limit will exist if and only if x belongs to the interval where minus 1 is not included and 1 is included, and that's your option D. Question number 22 is, we need to find this limit t tends to 0 f u plus tv minus f u upon t. Now u is 1 by 2 comma 1 by 2 and v is 3 comma 4. Now u plus tv, it will be 1 by 2 plus 3t comma 1 by 2 plus 4t. So we have to find this limit, which is limit t tends to 0 f 1 by 2 plus 3t comma 1 by 2 plus 4t and minus f 1 by 2 comma 1 by 2 by t. Now fxy is x square into y minus 1. So we can write this as limit t tends to 0 1 by 2 plus 3t whole square into 1 by 2 plus 4t minus 1, and then minus will be 1 by 4 into minus 1 by 2 upon t, which is 0 upon 0 form. Now before taking L'Hopital's rule, we'll write this as 4t minus 1 by 2. Now we'll differentiate the numerator and denominator separately. We can write this as limit t tends to 0, and this is 2 into 1 by 2 plus 3t into 3, and then 4t minus half, and then plus 1 by 2 plus 3t square into 4 minus 0 upon 1. Now if we put t as 0, we'll get this as minus 3 by 2 and then plus 1, which is minus 1 by 2. So answer to this limit will be minus 1 by 2, and that's your option C. Now 23 years, we are given a real number alpha which lies between 0 and 1, and we have defined a sequence such that xn plus 1 equals alpha xn plus 1 minus alpha xn minus 1. Now what we'll do is we'll subtract xn. We can write xn plus 1 minus xn will be alpha minus 1 and then xn minus xn minus 1. Now in the same way we can write this as alpha minus 1 square into xn minus 1 minus xn minus 2, and if we continue this iteration we can write this as alpha minus 1 to the power n x1 minus x0. So we can write xn plus 1 minus x0 will be alpha minus 1 to the power n x1 minus x0. Now in the same way we can write xn minus xn minus 1 will be alpha minus 1 to the power n minus 1 x1 minus x0, and finally we'll get x1 minus x0 as alpha minus 1 to the power 0 x1 minus x0. Now if we add them all up, on the left hand side we can write xn plus 1 minus x0, it will be x1 minus x0 into 1 plus alpha minus 1 plus alpha minus 1 square up to alpha minus 1 to the power n. Now what we'll do is we'll take this limit n tends to infinite. So it will be this limit n tends to infinite xn plus 1 minus x0, and here will be x1 minus x0, and then this series which is nothing but an infinite GP whose sum is a upon 1 minus r, which is 1 minus alpha minus 1. So it will be x1 minus x0 upon 2 minus alpha. We can write this limit n tends to infinite xn plus 1 as x1 minus x0 upon 2 minus alpha and then plus x0. So it will be x1 plus 1 minus alpha x0 upon 2 minus alpha. x1 plus 1 minus alpha x0 upon 2 minus alpha, and that's your option B. Number 7 is, by the binomial theorem we can write root 2 plus 1 to the power 10. It is this summation I varies from 0 to 10 ci into root 2 to the power I. And if we have to get it in this form, we have to write this as 1 plus root 2 to the power 10, and it will be equal to this summation I varies from 0 to 10 ci into root 2 to the power I. Now it says we have to find the value of I for which this term is the largest term among all the 11 terms. So basically we have to find numerically greatest term. Now we have discussed this in one of the previous videos. If we have to find numerically greatest term for x plus a to the power n, we will find some alpha which is n plus 1 upon 1 plus mod x by a. So in this case, if we find this alpha, it will be 10 plus 1 upon 1 plus, now x is 1 and a is root 2. So it will be 11 root 2 upon root 2 plus 1, or we can write this as 11 root 2 into root 2 minus 1, which is nearly 6.44. And we know that if alpha is not an integer, then its numerically greatest term is given by t greatest near function of alpha plus 1, which is 7th term. And if the term is 7th one, if we write the expansion, it will be 10c6 into root 2 to the power 6. So in this case, value of I is going to be 6. Now we come to its second part. It says, for every natural number n, let root 2 plus 1 to the power n be pn plus root 2 qn, where pn and qn are integers. Then we need to find this limit n tends to infinite pn upon qn to the power 10. Now if we take this limit here, it will be infinite. So we won't get any result from this. What we'll do is, we know that if we take the expansion of root 2 plus 1 to the power n, it will be c0 root 2 to the power n plus c1 root 2 to the power n minus 1. And if we consider root 2 minus 1 to the power n, it will be c0 root 2 to the power n minus 1 to the power 0 minus c1 root 2 to the power of n minus 1. So the expansion of root 2 minus 1 to the power n will be nothing but pn minus root 2 qn. Now we take limits both sides. Now root 2 minus 1, it lies between 0 and 1. So a to the power n in that case, it will be simply 0. And here it will be limit n tends to infinite pn minus root 2 qn. We can also write this as limit n tends to infinite pn upon qn. It will be simply root 2, and then limit n tends to infinite pn upon qn to the power 10 will be root 2 to the power 10, which is simply 32. Question number 57 is, consider the sequence an, and it is ea to the power 1 by n minus a to the power 1 by n upon 1 by n. Now we need to find this limit, which is limit n tends to infinite an. So we can write this as limit n tends to infinite, and then ea to the power 1 upon n minus a to the power 1 upon n upon 1 by n. Now what we'll do is, we'll let 1 upon n as t, then we can write this limit as limit t tends to 0 ea to the power t minus a to the power t upon t. Now this is 0 upon 0 form, so we can use L'Hopital's rule. So we can write limit t tends to 0 ea to the power t into log ea minus a to the power t into log a. Now we'll put t as 0, so we'll get this as log ea minus log a. So it'll be simply ln e, and ln e is nothing but 1. So answer to this limit is 1, which is none of the above, option number D. Now question number 58 is, let an be a sequence of real numbers satisfying mod an is less than or equal to 1 for all n. We define an as 1 by n, a1 plus a2 plus an. Then for n greater than or equal to 1, we need to find this limit n tends to infinite under root n an plus 1 minus an. Now we look at this limit, we can write this as limit n tends to infinite. Now under root n, now what is an plus 1? It is nothing but it is 1 upon n plus 1 a1 plus a2 plus an plus an plus 1 minus 1 upon n a1 plus a2 plus an. Now we'll take LCM, we can write this as limit n tends to infinite under root n. Now LCM will be n plus 1 into n, and here will be NA1, NA2 and NAN plus 1. So here we'll get NA n plus 1. Now NA1 minus n plus 1 A1. So it will be minus A1 minus A2 and minus AN. Now we know that for any AN, its modulus is always less than or equal to 1. So we can say this limit is less than or equal to limit n tends to infinite under root n upon n plus 1 into n, and here we can write this as n mod an plus 1 plus mod a1 plus mod a2 plus mod an. Now maximum value of any an is 1, so we can write this is less than or equal to limit n tends to infinite, and this is under root n. Now this is n, and then maximum value for each is 1, so it will be 1 plus 1 plus 1 up to n upon n plus 1 into n. So we can write this as limit n tends to infinite under root n into 2n upon n plus 1 into n. This n will cancel. Now power in the numerator is less than power in the denominator. So that means this limit will be 0. So from here we can say that this limit, it must be equal to 0, and that's your option number A. Now second form of Newton-Leibniz formula is when the limits are variable. Say for example, we have these limits as g alpha and h alpha, but this function inside the integral doesn't have this parameter alpha. Now again, if we'll solve this function, we'll get it as some function of alpha, say f alpha. Now if we differentiate this function, we can write this as f dash alpha, and it'll be equal to, now in place of x, what we'll do is we'll write this upper limit. So it'll be f h alpha into derivative of upper limit. So it'll be h dash alpha and then minus, now we'll put lower limit. So it'll be f g alpha into g dash alpha. So that is the second form of Newton-Leibniz formula. Now here the question is, we need to find this limit x tends to pi by 4 integral from 2 to secant square x ft dt upon x square minus pi square upon 16. So we have this limit x tends to pi by 4, this integral from 2 to secant square x ft dt upon x square minus pi square by 16. Now we'll put x as pi by 4, secant square pi by 4 will be 2. So this integral will be from 2 to 2. So we have 0 in the numerator, and then in the denominator we'll have pi square by 16 minus pi square by 16. So it is 0 upon 0 form. And when it is 0 upon 0 form, we can use L'Hopital's rule. So we'll differentiate the numerator and we'll differentiate the denominator. So we'll write this as limit x tends to pi by 4. Now here we'll use Leibniz integral formula. So it'll be f secant square x into 2 secant x into secant x tan x. So it'll be 2 secant square x into tan x upon 2x. Now we can cancel this 2 with 2. Here 10x upon x, it is not 1 because this is not x tends to 0, it is x tends to pi by 4. So we'll put the value of x as pi by 4. So it'll be f. Now secant square pi by 4 is 2. This value is 2. 10 pi by 4 is 1 upon pi by 4. So value of this limit will be 8 upon pi f2, and that's your option A. Now here the question is, we are given this function f which is continuously differentiable such that f2 is 6 and f dash 2 is 1 by 48, and it says if this integral from 6 to fx 4t cube dt, it is equal to x minus 2 gx, we need to find this limit x tends to 2 gx. So from here we can write gx as this integral from 6 to fx 4 t cube dt upon x minus 2. And now we'll take this limit x tends to 2. Now if we take limit x tends to 2, we'll get f2, and f2 is 6. So this integral will be from 6 to 6, which is 0, and then 2 minus 2 is 0. So this is 0 upon 0 form. And if it is 0 upon 0 form, we have to use L'Hopital's rule. So we can write this as limit x tends to 2. Now we'll differentiate the numerator using Leibniz integral rule. So it'll be 4 and then fx cube into f dash x minus, and here lower limit is constant. So derivative of lower limit will be 0 upon 1. So this limit x tends to 2 gx, it will be 4 f2 cube into f dash 2. Now this is 4. Now f2 is 6. So it will be 6 cube into f dash 2 is 1 by 48. So this is 12. This is 36 by 2. And this is 18. So value of this limit is 18, and that's your option A. Now here the question is limit n tends to infinite n square, this integral from minus 1 by n to 1 by n 2006 sin x plus 2007 cos x into mod x dx. Now what we'll do is we'll write this limit as limit n tends to infinite, this integral from minus 1 by n to plus 1 by n 2006 sin x into mod x dx plus minus 1 by n to plus 1 by n 2007 cos x mod x dx whole divided by 1 upon n square. Now this first function, it is an odd function, and if the limit is from minus a to plus a, then the value of this integral will be 0, and this function will be an even function. So we can write this as limit n tends to infinite to from 0 to 1 by n 2007 cos x, and then in this interval mod x will be simply x dx upon 1 by n square. Now if we put n tends to infinite, this is integral from 0 to 0, so it is 0, and 1 upon n square is also 0, so this is 0 upon 0 form. So we'll use L'Hopital's rule, and then where we'll differentiate numerator and denominator. So we'll write limit n tends to infinite to, and that will be 2007 cos 1 by n into 1 by n, and then derivative of 1 by n will be minus 1 by n square, and here in the denominator it will be minus 2 by n cube. Now minus and minus will cancel, 2 will also cancel, and n cube will also cancel. So we'll get this as limit n tends to infinite 2007 cos 1 by n, and it is cos 0, and cos 0 is 1. So value of this limit is 2007. Now here the question is, we need to find value of this limit. Limit x tends to 0, 1 upon x cube, this integral from 0 to x, t log 1 plus t upon t to the power 4 plus 4 dt. Now what we'll do is, we'll write this as this integral upon x cube. Now when x tends to 0, this limit will be from 0 to 0. So this is 0, and then in the denominator, it is also 0. So it is 0 upon 0 form. Now when it is 0 upon 0 form, we can use L'Hopital's rule. We'll differentiate the numerator. It will be x log 1 plus x upon x to the power 4 plus 4 upon 3x square. Now we'll cancel this x with x, then we can write 1 by 3 into, I will put x as 0 here, we'll get 1 by 4, and then this limit x tends to 0 log 1 plus x upon x, and this is 1. So value of this limit is simply 1 by 12, and that's your option B. Now here the question is, evaluate this limit x tends to infinite, this integral from 0 to x e to the power x square dx whole square upon 0 to x e to the power 2x square into dx. Now I've taken this question from a standard textbook. So I think this question actually should be, we have to evaluate this limit x tends to infinite, this integral from 0 to x, and it should be e to the power t square dt whole square upon 0 to x e to the power 2x square dx. Now this is infinity upon infinity form. So we'll use Leibniz integral formula. We write limit n tends to infinity. This is 2 into integral 0 to x e to the power t square dt into derivative of this function will be e to the power x square into 1 minus 0. Then the denominator will be e to the power 2x square into 1. Now here e to the power x square and e to the power 2x square will cancel. So we'll get this as limit n tends to infinite. This is 2. This integral from 0 to x e to the power t square dt upon e to the power x square, which is infinity upon infinity form. Now again we can use L'Hopital's rule. So we'll write limit x tends to infinite, it'll be 2, and then it'll be e to the power x square minus 0, and here it should be e to the power x square into 2x. Now e to the power x square will cancel. We'll get this as limit x tends to infinite 1 upon x, and 1 upon infinite is simply 0. So answer to this limit is 0. Now the question is, let A is nth power of this matrix 2 1 1 0, and we need to find this limit n tends to infinite a12 upon a22. Now let this matrix be B, and which is 2 1 1 0, and we'll write this as this 1 0 0 1 plus 1 1 1 minus 1. So this is I, and this is suppose C. So we can write this B as I plus C. So now we have this matrix C, which is 1 1 1 minus 1. Now we find C square will be 1 1 1 minus 1, and then 1 1 1 minus 1. Now we multiply. We'll get this as 2. Now this is 0. This is 0. And then it'll be 2. So C square is basically 2i. So once we have this expression, then we know that C square will be equal to 2i. And if we multiply it with C, we'll get C cube as 2c. And we multiply it again with C, we'll get C to the power 4 as 2c square, and 2c square is 2i. So there'll be 4i, c to the power 5, there'll be again 4c, and this sequence will continue like that. Now we have assumed this B is I plus C. Now we take nth power of B, then it will be I plus C to the power n. Now we can write this as B to the power n equals nc0 into I plus nc1 into C, nc2 into C square, nc3 into C cube, and this series will continue up to ncn into C to the power n. Now for even powers of C, it will be simply 2i, nc4 will be NC4 into 4i. So we can write this as NC0 plus 2 into NC2 plus 4 into NC4 into I, and then plus, now this is C. Now C cube is 2C, C to the power 5 is 4C. So we can write this as NC1 plus 2 into NC3 plus 4 into NC5, and it will be multiplied with C. Now we need to find sum of these two series. So this is our first series and this is our second series. Now say this is P and this is Q. Now we consider the expansion of 1 plus root 2 to the power n. It will be NC0 plus NC1 into root 2, NC2 into root 2 square, NC3 into 2 root 2. Now if we consider these terms, this is nothing but P. So it will be this P, and then if we take root 2 common, then it will be Q. So we can write this as P plus root 2Q. So value of P plus root 2Q will be simply 1 plus root 2 to the power n. And if we take 1 minus root 2, it will be alternate plus minus. Then we'll get P minus root 2Q, and there will be 1 minus root 2 to the power n. Now if we add them, we'll get the value of P. So we'll get this P as 1 by 2 into 1 plus root 2 to the power n plus 1 minus root 2 to the power n, and if we subtract them, we'll get this Q as 1 upon 2 root 2, and then it'll be 1 plus root 2 to the power n minus 1 minus root 2 to the power n. So now we have worked out values of P and Q. So basically we can write A, which is B to the power n, and there will be Pi plus QC. So this A will be this Pi, so it will be P0, 0 and P plus Q into C. Now C was 1, 1, 1 minus 1. So there will be Q, Q, Qn minus Q. So this A will be P plus Q, and this is Q, this is Q, and this is P minus Q. Now it says we need to find this limit n tends to infinite A12. Now A12 is first row second column, which is this Q, upon A22, and A22 is P minus Q. And it's given that this is equal to L. Now this is limit n tends to infinite. Now Q is 1 upon 2 root 2, and this is 1 plus root 2 to the power n minus 1 minus root 2 to the power n whole divided by, now P minus Q, and P minus Q will be 1 by 2, 1 plus root 2 to the power n plus 1 minus root 2 to the power n, and minus 1 upon 2 root 2, 1 plus root 2 to the power n minus 1 minus root 2 to the power n. Now we'll divide everything with 1 plus root 2 to the power n, and then we'll write 1 minus root 2 upon 1 plus root 2 as some lambda. So we can write this as this L will be equal to this limit n tends to infinite. This is 1 upon 2 root 2, 1 minus lambda to the power n upon 1 by 2, 1 plus lambda to the power n minus 1 upon 2 root 2, 1 minus lambda to the power n. Now this lambda, it lies between 0 and 1. So lambda to the power n, as n tends to infinite, it will be simply 0. So value of this limit will be 1 upon 2 root 2 upon 1 by 2 minus 1 upon 2 root 2, which is 1 upon root 2 minus 1. And if we rationalize, we can write this as root 2 plus 1. So value of L is root 2 plus 1. So value of L is root 2 plus 1. Now L square will be 2 plus 1 plus 2 root 2, which is 3 plus 2 root 2. Now we can write this 3 as under root 9 and we can write 2 root 2 as under root a. So value of a and b, they can be 8 or 9 or 9 or 8. Then the value of a plus b will be 9 plus 8, and which is 17.
Now let us take one question in limits. And this problem was asked by one of my students. It says let fx equals 8x cubed plus 3x and f inverse be the inverse of fx. Then we have to find this limit x tends to infinite, x to the power 1 by 3 upon f inverse 8x minus f inverse of x. Now what we are given is, we are given fx is 8x cubed plus 3x. Now we find f dash x will be 24x square plus 3, and it is always greater than 0. So that means this function fx, it is strictly increasing. And if we find f double dash x, it will be simply 48x. That means its point of inflection is at x equals 0. So this function, it will be strictly increasing function which will intersect the axis only at x equals 0. Now we have to solve this limit, which is limit x tends to infinite, x to the power 1 by 3 upon f inverse of 8x minus f inverse of x. Now what we'll do is, we'll say let f inverse of 8x is z and let f inverse of x be some y. We'll write let f inverse of 8x equals z and f inverse of x as y. Now we can write f inverse of 8x equals z as 8x equals fz. Now what's fz? Fz will be 8z cube plus 3z. So we can write this as 8x equals 8z cube plus 3z. Now what we'll do is, we'll take 8z cube common. So we'll write 8x equals 8z cube 1 plus 3 by 8 z square. Now we'll cancel this 8 with 8 and we'll take cube root both sides. We can write x to the power 1 by 3 equals z 1 plus 3 upon 8 z square to the power 1 by 3, or we can express z as x to the power 1 by 3 upon 1 plus 3 by 8 z square to the power 1 by 3. Now in the same way, we can solve this other condition, which is fx equals y. We can write x equals fy. Now fy is 8y cube plus 3y. Again we'll take 8y cube common. We'll write 1 plus 3 by 8 y square. And if we take cube root again, we'll get x to the power 1 by 3 and it'll be equal to 2y 1 plus 3 by 8 y square to the power 1 by 3, or we can write y as x to the power 1 by 3 upon 2 1 plus 3 by 8 y square to the power 1 by 3. Now what we'll do is, we'll put the value of z and y in this limit. Now we can write this limit as limit x tends to infinite,
x to the power 1 by 3 upon z minus y. Now z in this case is x to the power 1 by 3 upon 1 plus 3 by 8z square to the power 1 by 3 minus x to the power 1 by 3 upon 2 1 plus 3 by 8y square to the power 1 by 3. Now we can cancel this x to the power 1 by 3 from the numerator and from the denominator. Now we have to find the value of this limit z and y when x tends to infinite. Now z is f inverse of 8x and y is f inverse of x. Now this function fx, it is an increasing function. So as x tends to infinite, fx tends to infinite. And if we talk about inverse function, its inverse function is nothing but it is reflection of fx about y equals x line. Now for inverse function also, when x approaches infinite, f inverse will also approach infinite. So it simply means that when x tends to infinite, z tends to infinite and y tends to infinite. And if z and y, they both approach infinity, then in that case 3 by 8z square will be 0 and 3 by 8y square will also be 0. So value of this limit in this case will be 1 upon 1 by 1 minus 1 by 2, which is nothing but 2. So answer to this limit is 2. And that's your option C.